Good morning, sir. That's a good morning. Sadish, Sadish,
सर
shall we start?
इप्पो स्टार्ट है सर
Okay.
Good morning, everyone. Thank you for joining with us. We'll wait for a few minutes for others to join. We'll start the session.
Sadish.
A very good morning to one and all. Myself, Sahla, will take this immense pleasure to welcome all for the second day of short-term training program on the topic Smart Computing Technologies and Applications, organized by CAC Department of MES College of Engineering, Kuttipuram, in association with AICTE. I also welcome Labbasar and KP Muhammad sir. Hope you had a great time yesterday. The Internet of Things is taking the world by storm, as it has become one of the most influential buzzwords, not only in the tech sector, but also many other businesses. From farms and factories to smart cities and homes, IoT technology is continually expanding set of connected systems and devices. While cloud computing has made it possible to process massive amounts of data, it won't be an ideal choice for all applications and use cases. Am I right? Yes. The answer to address all the limitations associated with the traditional cloud computing infrastructure is something called edge computing. Today's session is on edge computing and optimization. With great honor and respect, may I invite Dr. Manish T.I., Professor and Dean PhD Program, Adishankara Institute of Engineering and Technology, Kaladi, India. He earned his PhD and Master of Engineering from Manomaniyam Sundaranar University, Tirunelveli. He had several years of work experience as assistant professor, lecturer, software engineer, and so on. Let me hand over the session to you, sir.
Just a minute.
Okay, sir.
Good morning, everyone. A warm good morning to everyone, and also respected dignitaries, principal head of the department, and the coordinator of the program. My topic today, our discussion is like the edge computing and optimization. And I have taken the perspective of the image processing, like how the edge computing and optimization happening in the image processing perspective. Again, the image processing perspective means this kind of processing was done in the cloud for a better performance. And we are basically looking at one of the application of image processing as edge computing. It's a pre-processing step. Later, it goes for the segmentation and the classification. But here we will be more looking at the edge computing basic technique, how it can be collaborated with the soft techniques, how it will be enhanced to the hybrid methods. When it comes to the hybrid methods and soft methods, this process becomes very tedious, and this can be done in the cloud platforms. So first we look at the basic edge computing techniques. Later we'll go for the optimization part. When you start with an edge, whether you will be storing the image in the local drive or in the cloud, wherever you are processing it. It's basically the conventional way of thinking is that it is a sudden change in the intensity. In whether in a grayscale or in a color image, is purely a sudden change in the intensity of pixels. And different methods will be there, and different methods yield different results. Someone will be useful information for you. Someone will be not relevant to you. And also there will be a discontinuity in the image brightness or contrast. Like in the image what we have shown, the foreground there is an house, and background there will be a different color. So that's a brightness difference will be there, and we can identify an object out of that. And there will be the edges basically occur the boundaries between two regions or two objects or any two things of our interest. So there exactly the boundary will be having an edge occurring in the image. And we can see some images over here. In a house with a background. We have a house with a background and another set of some wall-like structures, and we have a background white color. And everything there will be two regions. In all these two images, we have a two region, one foreground and one background is there. And also there is a contrast difference in the two images. Behind the house there is a contrast, on the house there is another contrast. And the intensity change is also happening abruptly. So these all things contribute to the edge. And we already said that the edge starts to the basic step for the segmentation, and segmentation is the basic step for classification. And classification nowadays is one of the major area where everyone is concentrating, whether it will be an image, whether it will be when it comes to the text, or when it will come to a data, it is called as data analytics and data classification, the big data, some kind of things. When it comes to image, we will call as image processing, image analytics, something like that. So it's a pre-procurement step in all the process when it comes to the image. Data, the type of, instead of it, we have different type of classification, like methods are there, how we will be classifying the data into different segments and different clusters. Later it will be optimized for you as a business information for the later stage. Image also have some major application, like the edges can be taken care for a medical imaging, where we will be identifying the different diseases, the possibility of diseases, and there the edge play a major role to identify the different diseases, to segmenting out of the tumor and all kind of things in medical imaging processing. It's a major thing. And also when you go for an application like satellite image processing, when it comes to a satellite image processing, the relevance of the edge is also very important, because we will having a different geographical structures given to you, and you are going to identify whether the structure is a road or a building, and you have to go for a further planning. And different natural resources also we can identify using satellite images without a higher band, which are provided by corresponding ISR or NASA, whoever may be. So there also we have a relevance. The application have a very relevant to this edge. And the basic thing is edge. Anyhow, we have well-defined methods, automatic methods nowadays for edge detection. But when you create an application which are specific to you, you should not find any common method for an edge detection. In that point of time, you should be able to create your own custom method for your optimization. So there is global methods are there for edge detection. But at a point of time when your application are unique and you require a specific result from your own application, then you go out for a custom edge detection methods. Whether you cannot have the conventional methods to help you to get a better result. So that's the relevance of the edge when it comes to this processing environment. In whichever environment, the data or image, wherever environment the processing has better relevance. And why this image is getting this much of prominent value means the images, like we will be having seen a recent trend going on, like whether it will be related to this or not. we have a recent trend of shifting from an text-based social media to an image-based social media. And the evident result is like we started with Twitter, we have a Facebook. Again, the trend is going for Instagram, and more images are getting involved, and more than text, everyone knows keep on investing on images. Whenever this kind of a large amount of images are there, we have a requirement of identifying what the image is, whether it is not in align with the legal requirement or something like that. Again, we require this kind of processing and everything and monitoring for this kind of things. So the relevance is increasing for image. At the same time, also the data part also for the business analytics, the data part also having a better relevance nowadays. Now we need to come to the basic fundamentals of edge detection. Like to identify edge, we have some descriptor for that. So basic we will call it as a parameter or edge descriptors, which provide you some insight into the edge, and we have some vector related to the edge detection, and we call it as an edge normal, which define the vector, which define the direction of the maximum intensity change. When there is a pixel is there, we know that the basic unit of an image is a pixel, and we have 8 neighbor to the pixel is there. There will be an 8 neighbor across the image for each pixel. The border pixel will don't have an 8 neighbor. Anyhow, we'll add the pixel to that. And when there is an 8 neighbor for a pixel, we have to identify which region of this 8 neighbor have a maximum intensity change. So we create a vector for that. And also the direction, which is perpendicular to this edge normal what we are creating. And we have a edge position or center, exact position where we are shifting from one edge to another edge. Then strength of the edge, like how the change is happening, how the contrast is changing. So there we will call for an edge strength. So these are the 4 parameters which are basically taken care of in our edge detection methods that we call as a gradient methods. So we will be more focusing on this kind of methods, and this parameter will be well taken care of in the gradient methods, that is first derivative edge detection methods and also second derivative edge detection methods. And again, the edge detection usage, and we have described in well, like what are the usage edge detection. Basically, previously it was a part of an module just talking about edge detection. Rather than that, relevance has gone increase, and we can any region of interest to crop it out from an image we require an edge detection. And also the important thing is that whenever you go for an image, and if you are not able to preserve a structure, and when you get an extracted image or the edge detected image with losing its information, it is not useful. So how much data we can retrieve from information we can retrieve without changing the structure of the image. So that's one of the things. And also you can recognize object boundary segmentation as part of the computer vision and the recognition. And the recent trend, we have a new emerging technology like robotics. So robotics, the decision making part is AI, but to get for the decision making, the robotic vision should be given a prior importance. So the robotic visions will design which task should be taken next, what to, where to move, what to do, and the kind of things. Whether it will be processed by an AI, artificial intelligence, but the basic input for this is images. And other sensors is also the temperature, humidity, those kind of sensors will be also there. Anyhow, one of the major parameter providing to the processing part is the image through the camera. So the relevance has very high. And also we can identify the corner lines, curves, and everything. And we can identify this thing from the images. Now, based on the how the intensity changes, we can divide into different edge types. We can say that this is of this type and this is of this type. Like that, we can divide our image processing or segmentation methods or edge detection methods in common with some types. And the type will be basically looking at the intensity profile change, how the intensity profile is changed. Based on that, we can have the different types of edges. And the first one is step edge. So step edge, what we exactly define what is an edge. Totally, there will be a abrupt change of intensity. Like we know that we have a grayscale image, and we have a grayscale image of intensity 0 to 255. Think of that the first 1 pixel is 1, the intensity value is 1. Suddenly the next pixel is nearly 100. So there is a change of 99 grayscale value. It is changed from 1 to 100, sudden change. That is called an abrupt change. And 1 to 5 is not an abrupt change in a scale of 0 to 255. In a 0 to 255, when there are changes in an 100 value, it's a sudden change, and it's an abrupt change. In that kind of an edge, it is called a step edge. Then there is a ramp edge. We have another type of edge which are occurring ramp edge. The change is in a continuous instant in a way, not in an instantaneous mode. So continuous way means we have a pixel, 1 pixel having some intensity value here on 100, and the neighboring pixel, what we call 4 neighbor, for an example, 4 neighborhood. The pixel having an intensity of 120, again the 4 neighbor of that pixel having an 130, again that 4 neighbor of that pixel having an 150. Similarly, the change is happening, and change is slow, but it is happening. When you go for a 5 to 6 pixel neighborhood, 4 neighborhood, then it becomes 100 to 200, and that is called a ramp edge. So we are talking about in a grayscale 8-bit image, the scenario we are talking. Then we can call it as a ramp edge. Like we start from 1 pixel, and that is 100. The next the 4 neighbor, the topmost position of 4 neighbor having another 120. Again, that pixel 4 neighbor having 130. Similarly, think of like that, and it will come to an after 10 pixel it will go into a 200. That's also a change which are occurring in a continuous way, but occur in a finite distance. So we can have a 10 unit distance. We can call it as a 10 unit distance from the original pixel, and that we'll call a ramp edge. And we'll having ridge edge. Ridge edge basically comes in the form of an when there is a like we have an image called that we scan when you buy some product we scan some images. We have some the vertical lines, a barcode reader what we have, and that is an image. Barcode reader is an image, and when you take an edge for the image, and that type of edge is a ridge edge, because suddenly there is an intensity change, but it will not last for long. It may be like the barcode reader, we have the vertical lines over there. Suddenly it falls back to the original value, because suddenly it got the darker shade. Suddenly after the line segment, it again fall to the white. So there we call it as a line. It will be representing some kind of line, and that is called a ridge edge. So it will be the initially white will be there. Suddenly 255 to 0 considered as a black, the pixel value as a black, and 0 will not last for 1 or 2 pixels, because the vertical lines are 1 or 2 pixels. Again it will come back to 255, again it will come to 0, again to 255. So that kind of a pattern will be followed in the ridge edge. And another type that we know as is the roof edge. And roof edge also will happen in another form of a ramp edge, but it will be reversing. It's another form of a ramp edge. The process of changing is not instantaneous. It's in a continuous slow manner, but it will also do a reverse process also. It will go up to like 100 to 200 it will come the value. Again from 200 to 100 it will come in another slow process. So it's a reversing is there. In ramp edge we have only one side operation is there, like 100 to 200. But here the roof edge will be reversing the intensity value from 100 to 200 and 200 to 100. And basically it will happen in the case of different surfaces or different object intersection is there. This kind of a roof edge will be activated. So this information will give an insight how the edges is there and how it is going to help us in our detecting an image or understanding an image in a better way. And these are some basic steps which the edge detection. Or in the edge detection, when you take edge detection as an entire process, we will be having a smoothing operation. Smoothing operation, which basically thinking of and removing noise. In modern scenario, the noise in indulging into an image is very rare. Still, there is a possibility of a noise in some application. When you do an industrial camera and when you try for an image capture, there is a probability of a noise due to some interference and all kind of things. But when you go for an defined way, commonly the noise indulgent into an image is very rare. And also in the satellite images also there will be a possibility of some noise. Due to some technical reasons, there will be a possibility of noise. Otherwise, the noise in building, because the modern days, the image capture system are so fine that the noise probability is very less. Second one is enhancement. Enhancement, again, we will be sharpening the image so that we can extract the feature of this detection of the edge pixels. We will be identifying the edge pixels, and also the last part is the localization. The location of the edge will be defined after the edge map. We will be segregating that to create an like a location of an edge. And again, we can go for after identifying the exact edge, again you can go for the edge thinning and linking, which are linking means when there is a misses in the edges, non-continuous edges are there, can be connected based on some probability or based on some assumptions. So these are the basic steps in image edge detection. Now, when you look at the edge detection, the types, we have a broad area starting from classical gradient to wavelet, Gaussian based, and then comes the soft edge methods like fuzzy logic, artificial movement network, particle swarm optimization. Then comes the genetic algorithm. Then we have a hybrid. And the conventional way of the edge detection approach, what we call as the classical gradient, the wavelet, and the Gaussian based filters, which are not exactly made for a particular application, but they are for general purpose, and it will be used by everyone. When you go for an image processing fundamentals and all, we will be using this kind of filters or this kind of edge detection methods to crop the edge out for any image. Basically, we will do for the images which are standard images, like what we do for the Canny edge detection and Sobel and Privet robot, and everything we will do for the standard images. But when it comes to the fuzzy logic, the artificial neural network, and the genetic algorithm, which comes next to this kind of methods, which we call as the evolutionary methods, evolutionary edge detection methods. Again, we have the particle swarm optimization, which replicate the behavior of the insects and that kind of animals. And again, we have a hybrid method also. So this is the entire method categorization we have. So we look at the base first. We look at the basic methods in the edge detection that will be done in a conventional way. Then we look into some of the evolutionary methods and overview of the evolutionary methods. Then we will go think of an hybrid methods and how the hybrid methods give better results, not sticking on the conventional methods or evolutionary model. When hybrid methods are there, it will be more suited for your customized application. For doing testing, it's okay with the conventional methods, but when you go for an application, when you created a product and you require an identification for that product, you're not looking at the general features of the edge, you are only looking at the features of the edge which are relevant to your image. So we can have a better customization in the process of the edge detection, whatever thing may be, scaling, thinning, whatever operation may be, and you can create a hybrid. So we commonly, again, the canny edge detector is one of the optimal edge detectors, so I given a separate class for that. Again, it just comes under this the zero crossing methods only, but again, I have given a separate segment for that because it is a well-known edge detection method, commonly everyone acknowledge. So we have the gradient methods. Gradient methods, we're only looking at the first order derivative. Commonly we call it as a first order derivative. And when it comes to the zero crossing methods, we call the second order derivative. And KH detector also comes in this category. Again, that will be considered as an optimal one due to their features, their localization features and better edge detection features. They are considered as an optimal one. Then there is another class of GNet soft computing altogether, like ANN artificial neural network, PAM optimization, SWAM optimization, support recognition, genetic algorithm, ACO, and coordinate optimization. Again, it comes as PSO. So this is a classification we have. And when it comes to the gradient methods, how we create an edge out of that is that we will take the local maximum and minimum using the first derivative of an image. Again, image is a set of values. We have a mathematical representation for the image, so we can do that. And also we compute the gradient magnitude horizontally and vertically. Both horizontally and vertically we will be using gradient magnitude, and there is an equation for that. And that we can refer from the literature. And when it comes to the zero crossing method, we will be identifying the zero and the second derivative of the image, and also it will be based on the Laplacian of the image. We will be getting the zero crossing method or second order derivative. The working is based on that, and basically the zero crossing methods will be looking at the Laplacian representation of the image, and also whenever there is a second derivative is zero, it will be locating an edge. So this is the way gradient and the zero crossing methods works, and this is a classification, ideal classification, how it happened. And again, I said the Gaussian based is the canny is a Gaussian based, but I categorize it as because it is an optimal one, recognized and appreciated by everyone. We are given a separate place for the canny. This is the gradient based and Gaussian based classification. So I will prevent and Robert, and also when it comes to the Gaussian based, we have the Laplacian of Gaussian, and it's a different. Also, one more name is there, and also we have the canny edge Gaussian. So this is a classification. The conventional way of classification into two, the first order and second order. And we are well versed in the MATLAB. We are well versed the functions. Edge function is there with the parameters of a private and robot to do the operation to find the edges, and sample images also there. And for also and the Laplacian function also we have defined functions are there in the MATLAB, and OpenCV we also alternatives are there. We will not look into the how the operator works and all like conventional way of methods, but we are more focusing about their advantage and disadvantage. And we will look into this hybrid methods and the ACO methods or particle swarm optimization methods. The Sobel operator basically comes under the first order derivative. Simple, the time efficiency easy for smooth search and all edges we can identify easily. But because it will be looking when you talk about this Sobel operator or the first derivative, you are taking gradient in the horizontal and vertical directions. Then we will be missing the diagonal directions. So that is a disadvantage, one of the major disadvantages in diagonal direction will not be preserved well, and it will be sensitive noise, and noise are there, and that edge rotation is not up to the mark, and thick and rough edges do not give block result. So these are we have more weightage to these limitations when compared to the advantages in the saw block. Okay. Then again we look into the another one of the first order derivative. Again, it will be good at vertical and horizontal edges because we are taking the gradient value for the horizontal and vertical. So it will be ideal for that. And it will also ideal for the orientation also. When your image contains the vertical and horizontal types of objects, then this oblong fluid will be working very accurately. Like there is an image of an house, what we have seen. And house we don't have any curved or any type of other structures, only the horizontal and verticals are there, either rectangle or a square. When you take to a unit level, either rectangle or square is there, it will work efficiently. And the limitations, what we're looking at, the magnitude of the coefficient is fixed and cannot be changed. The coefficient is defined one. Again, the diagonal directions will be a disadvantage. Robot operator also again comes under the same method. The method is very easy. Here the diagonal directions are preserved, but sensitive to noise and not very good at edge rotation. So these are the limitation of this. And this comes under our Gaussian, and we have another name in the operator, will be LOG operator, something like that. And it can be detected in very non-orientation. Again, sensitive to noise, the limitation, localization error is there, local minima error, what we call, and also finding unwanted edges as edges, because in the image it is not an edge, but due to the noisy responses, it is created as a false edges, and it will go for the all direction. It's a better, it's a characteristic in all the direction. Then we look at the one of the optimal methods out of this both category. We call as a Canny edge. Here we have a good detection. The maximum detections will be there, and we will be minimizing the false positive and false negative, unwanted types of representation. We are minimizing, and the localization of the edge is there. When it comes to the true edges, the localization is very good, and return only 1 point for each edge. Only one response will be there. The multiple response scale, we have 3 scale response in the Canny, and each response will be dedicated for an edge, and that will not have any further like overlapping of edges and that kind of things. So ideally, it is an optimal candidate. When it comes to the conventional methods, it's an ideal candidate. Again, we look at the limitation. We know the advantage, but when you look at the limitation, we have a false zero crossing error will be there. When it comes to the complex commutation and time consuming, there is also a limitation. The complex commutation means we have a complex images with different type of edges, a different scenario, different contrasts. Again, the Canny operator fails in that. So there, the community come forward for the better edge detection methods, and these are things. Again, the repetition of hardware, the limitation of all this method altogether. We have this kind of a limitation problems in edge detection. What we have, and again we require at something called an again we require a threshold level, in which we can say that up to this threshold only there is an edge, something like that. For identifying that, there is a problem, because by the introduction of the noise also, the threshold, there will be change in the threshold. So when you put as a threshold as 10, and there is a noise in between the edges and the image, we incorrectly consider it as an edge. So that's a problem with this kind of edges. Okay, so these are all together limitations of the edge detection methods, and also this is basically with the gradient based agility. The corners are missed, and again the threshold value we have issued different operators for different features. So these are the disadvantages. And this is one of the demo you can see when you go for an edge data. So we will just try that demo. You can try it from your side also. So we have a demonstration like that, and a small demonstration, because when you talk about the canines, the budget, data, we are just having something and different stages. Can we look at different stages? We can put the sigma value. The better the sigma value, we will be able to identify, and the threshold value will be setting the high threshold. And we can, each step by step, we can go, like what happening exactly. After smoothing, what happens? The next direction, right direction. And also suppression, the steps are in the end, the thresholding, after thresholding. And we can see in this side the advantages, like if you threshold, we increase the threshold, and what happened, we can identify. So what we see that the level of threshold, the threshold setting is one of the major role when you go for any this kind of conventional way of edge reduction methods. So that have a very significance, and this is SNR, the signal to noise ratio. They have provided some signal to noise ratio to you, and we can other overlay over. So the thresholding is one of the major parts. So when you give an incorrect threshold, because if you are familiar with the MATLAB, you have to provide the threshold, or the digiter will take by default value of the threshold. Then what happens is that the image you are provided will be of a different nature, and you have to assume the threshold, or you have to go for an auto mode, which may not be ideal. So identifying the threshold is one of the major hurdles when you go for an edge reduction in a conventional model. Okay. So you can try it out, and I've already taken the values they are given, pixel value and everything. And also you can try it from your own input also. It's up to you to identify some examples and how to work it on. And so I only use, because the other operators are not up to this mark, so there is need not for a demo for that kind of an agitated test. After this fight, the canny will be having a better one. So we have seen some demonstration. You can try it out from your side also. Okay. So I will be providing this in your chat box there. Yes. This will be given in your chat box. You can try it from your end. If you have time, you can try it from your end also. Again, coming back to what the discussion is there. So that we are seeing a conventional way. Now we will be looking to the major part, that is soft computing methods, or we can say the evolutionary based methods. And the first thing is the fussy way of doing the things. And we know that we are fussy means there will be a fussy membership function will be there, and also some rules will be there, and based on the rules we will be defining the edge. Okay, so the degree of fitness in the neighborhood, everything will be there in the membership function, and the function will define something rules, and based on the rules you will getting some results, and these results will be identifying whether this is an edge or not. So that is a rule based approach will be having the fuzzy membership function, and corresponding rules will be helping, and it will be basing on if then rules. It is very flexible one. We can set your own things. Again, there is a problem of thresholding comes. If you don't know which is a higher threshold or threshold you have to put, there is an issue with that. And the major problem is that the fuzzy nature, the computation is very expensive. Means that when you start a fuzzy operation for an edge detection, it will go for a long time without any result. Because based on your conditions, it may go for a looping, it may go for an ununded task, and the tedious task. And without also an end result will not be also an optimal one. It is an edge detection without any relevance, you get an edge. So there should be also, we have to very clear about the fuzzy rules you are setting and the membership function you are setting in the fuzzy. Otherwise, it will be up and toes. And the rules commonly do it like this. We have an 8-9 representation of the pixel over there. And you talk about that the first pixel will be having, and we say that all the bottom, middle, and the middle left pixel is in black, and all the top corner, the pixel is, the corresponding pixel is white. Then that entire pixel is represented as a black. So this is something in sample rule I have given. Similarly, based on your requirement, you will be setting some rule. And when the rule is correct, you will be putting this as a black. So you will be looking at this. That is an if-then condition. But in if-then condition, instead of numbers, we will be putting the pixel value. When this position, out of the same position, this position, or this combination, we will put as black, or we will put as a white. All other conditions will put as a white. That is else, it is white, all other conditions. Likewise, we will be putting something based on some threshold. We will be defining some fuzzy rules. Again, the rules is set by human, and the membership function suitable for the application will be set by us. Again, make a difference, because that will be only based on the personal knowledge and the personal taste. They will put these conditions. Again, it may go for a toes and something like that. Again, when it go for a gradient, this kind of rules can be, we can say, like the x direction and y direction, we can find. We can say that we can go for a vertical and horizontal gradient. We can take. Similarly, here also, like we can set some rules, like if the gradient of x is low, gradient of y is low, then net strength of e comma x comma y is low. Something like that we can define. These are the if-else rules we can set. Some other the rule, another set of if-else condition. There we have seen as pixel intensity if-else condition. Here we can see the gradient value, and we can consider as a rules if-else in horizontal and vertical direction, gx of gx and gy. And based on that also we can create some kind of an integration methods. So here the main depends on the fuzzy set and the membership function and the rule you are providing. Without a proper choice, you cannot detect the true edges in the fuzzy. Even fuzzy is a complex nature, but when you come to the edge detection, again the same problem will happen. For that, we have a different approach. To overcome this issue, problem with the fuzzy logic methods, we will be adding it with the particle swarm optimization methods along with the fuzzy. As a fuzzy individual detection operator, it's not up to the mark, and we have this kind of a restriction. But when you combine with the particle swarm optimization, and if you are able to get an exact initial edge map from the particle swarm optimization, it will be a better for your fuzzy. Okay, so that is one of the things that we can go for an hybrid. When you have a fuzzy method, the particle swarm optimization, however, it brings you an initial edge map. That we can add up with fuzzy, and how we will be adding up, we'll see in the later. Now we will be talking about the fuzzy edge methods and how it fails due to the personal choice what we make. Okay. Then approach, we are having the neural network approach, or what we call as artificial neural network. We have a network connected to it, and the network will decide what to do and how to get the edges of this kind of things. and for organization, for hand feature map, for which is for clustering, kind of things. But here we are going to discuss a neural network we call as fast forward neural network, which are a two-stage neural network, which are basically for finding the edge detection. As an example, what we are taking when you go for a neural network approach, two-layer hidden layer neural network. So first layer will be providing you the feature enhancement, and the structural boundary extractions will be taken there. The first stage we will be doing the traditional supervised back propagation network, and second one is designed without training. So the training part is we have neglected in this part, and it will be working very fastly, and it have an RDR implementation. So that's the implementation part. What we are looking at is how it will be happening. So edge enhancement will be done in the first stage, and second stage will be identifying the edge. So look at this is the way the neural network works, and the first is for the edge enhancement, and second is for the boundary expression. So the gray level image, we have in the first edge enhancement network, and the first part will enhance the image. After first part enhancement, it will be given to the second network pool of nodes, which will be extracting the boundary, and we will be providing attributes, and initially we'll be the input gray level image, and finally we'll get an edge map of zeros and one, etc. So this is the way neural network works. Again, the thing is that when you feed into this hidden layers, for enhancement, okay, we have some parameters will be given for the FNN. But when you go for a boundary extraction in the neural network, again, what the parameter we are going to give, what the threshold you are going to give, what the dates you are going to give, that is decided by the human beings. Again, based on the image, there will be a probability of fault occurrence. You are giving incorrect threshold or incorrect parameters or incorrect weight to this boundary extraction. And again, the edge map you are getting a different. Any of the processes a new evolutionary method, but inputs you have to give. It will be not in a creating from its own knowledge. So again, we will have issues in the neural network also when it comes to an final edge. Maybe not an optimal one. And again, when it comes to a neural network, the processing is tedious, the time taken is also very high. Whether it's a FNN fast forward neural network also, the number of processing will be happening because the edge enhancement and boundary extractions are a number of nodes, and how they work, it will be very time consuming. And this is the way artificial neural network or neural network works in the edge detection methods. Then comes the evolutionary algorithm. And fuzzy and the neural network, we cannot say it's an evolutionary. Again, it comes under the initial part of the evolutionary system because the fuzzy logic implementation, everything comes in the initial stage. And in the evolutionary algorithm, what we need to think is that we are finding an optimal solution to all the engineering problems. How to find an optimal solution for engineering problem? Whether it will be edge detection, they're talking about objective function, pattern recognition, image processing, filtering, modeling, everything. The complex problem can be solved. So when it comes to the evolutionary part, we have some, and all this evolutionary part started from the thinking from a fuzzy logic nature, from a crisp fuzzy logic nature and the artificial neural network, which simulate the brain, the way of working of the brain. And up to now, all the methods what we have seen that we cannot solve methods cannot solve all the problems, or a solo method or one method cannot solve all the problems. Whether it will be a conventional way, or whether it will be a fuzzy or an artificial neural network, we cannot solve exactly all the problem here. For the sake of edge detection, we can do, and we can try it out some different threshold value, different weights, and we can get an optimal result. That is exactly good for a research, or when you go for an academic research, it is okay. But when you have a product or an application which require an exact result in the first try itself, like you have an like we have an industrial problem of identifying the fault components in a product, and the belt conveyor will be moving, and you will be taking image of the products. So sudden moment, the faulty things will will move across, and your detection is not able to find that edge or the small crack in the object. It will be a major hazard for your industry or your product. There is no second chance in there, where we can try it out once more. We can give it the different threshold, and whether it is an edge or not, we can find it. There is no second time in there. So some application there will be no second chance is there for giving different threshold, different parameters, and you try it out or a better result. When it comes to an academic perspective or academic research, what we will do is that we will be providing trying out different threshold, different alpha value, gamma value, concept values, and we will find an optimal one. And the result we are getting is an optimal, and we will have a better publication or something like that. That's a different scenario. And when it comes to an industry perspective or business perspective, it's a different thing, where there is a no second chance, no second choice for it. So when you detect something, it should be an ideal one. It will be nearing the optimal or nearing the perfection. So that will be our optimal. Then the third comes the evolutionary algorithm, or what we call the like the particle sum optimization, which is basically behavior of the animals. One is bacteria foraging algorithm, which will be looking at how the bacteria are moving across and how the birds moving across, and also genetic algorithm, like the different operations like chromosome mutation, crossover, different application is happening, and whether that can give any good choice for us in their generation. And genetic algorithm is also a randomness is there, because the crossover and mutation may not be relevant to what the problem we have, because we do some operation like crossover in some binary digit. We are setting a two set of binary digit, calling it as a parents, whether it may be binary digit of our image, grayscale. But we call it as a two as parents, and we'll cross over it and we'll mute it and we'll get another value, which are not relevant to image to the image intensity, and we will get as an optimal result. So there are also some unpredictability is there. Again, randomness. It comes in that genetic algorithm. But when it comes to the particle sum optimization or the animal behavior, what we doing is that we are just relating this animal behavior to the problem we have. The ideally thing like we have flying devices like Apache, that we are taking from different animals like hummingbirds and something like that, how they fly, something like that, and we study the same pattern and implement in our hardware devices. So these kind of things give an motivation for everyone to take that concept from the animal to the common science process. And one of the process what we call edge detection also, we have a similar process. And one of the ideal example is the ant colony detection, the behavior of ant for foraging to food, and that is replicated in our process. So we'll see some of this. The bacteria foraging algorithm. The movement of the bacteria is the ideal condition for the this algorithm. And instead of bacteria, we consider it as our data points or our image points. And the bacteria, what they do is that they forage here and there, and they require maximum energy spent during the forage. And we will find the coastal code by the bacteria in terms of the food. And any animals can come there will be foraging for food only. So that will be the basis for our thing, and we will find an optimal cost out of that. And there is some technical process, chemotaxis, forming, reproduction, elimination, and dispersal. And here, elimination will consider as a bad pixels or bad data points will consider as an elimination. Sometimes the good data pixel may also get eliminated, but we'll think it as a bad data point. And we'll go for an optimization process. Whether the problem get optimized or not, we don't know exactly, but the process will follow. And in bacteria foraging, the algorithm, they claim that the edges are accurately detected. This cannot edges in a figure and they get joined. That's okay. That's one of the things, the major advantage of this animal behavior algorithm. Like, when there is an edge is there and there is a missing edge is there, the orientation of the edge, the direction of the edge, and the magnitude of the edge will be taken, and it will get corrected by this foraging nature of this bacteria. That's an ideal thing, because when you go for a scratch from an image and if you're trying to detect an edge out of that, it may not be a successful way of doing that. But if there is a disconnected edge is there, and if the disconnected edge we can make it forge, the bacteria get forged and we can connect it together. And we have two edges will be there, which having their own magnitude and their own direction of direction will be there, and we can calculate it and we can forge the bacteria. That's an ideal thing we have to do. And also the bacteria or whatever the animal behavior, we can forge this parallelly. Because when it comes to a parallel processing, nowadays we have a parallel processing processes, parallel processing architecture is there, parallel processing operating system is there. Everything is in a parallel process. Time is money nowadays. And when it comes to a critical application, we can go for a parallel processing. When the parallel processing concepts are there, even the NRA concept of the MATLAB or Python, we have a parallel processing architecture is there, where we can have a parallel processing of the, so we can release n number of bacteria, and each bacteria can forge parallel in an image. When the bacteria forge a parallel image, different outcomes will be getting. The process becomes faster. Each having each thread, each bacteria considers each thread will process inside the image, and you will get an optimal result in terms of time. So that's one of the advantage of this kind of animal forging behaviors. And here also we can say that they itself saying that there is a possibility of error is there. The outcome will be error, because it cannot be a standalone method for your edge detection. It can be an enhancement of your edge. We can detect some edge from some method, a conventional method or a gradient method or a classical method. Then you can put on this kind of a forging algorithm to cross check that the image is accurate or not, and the disconnected parts can be connected, and you will be getting a better result out of that. So standalone method, we will not recommend the evolutionary methods, but as a supporting method or an enhancement method for an edge, for a better result, we can go. Again, the edges which are small, incorrectly created edges also, it can forge and it can find that whether it is correct or not, or it can reject that edges also. Then come to the genetic approach. Genetic approach, again, the main thing is that in case of an image detection, we have an image, we have a pixel, the pixel have a location. The main thing, the genetic algorithm, we have a location, and location has not much significance in genetic algorithm. The genetic algorithm mainly focuses on the value of the pixel, and that will be considered as a parents, and the parents will be selected out of that. Selection will be done. Again, it's a human interpretation. The selection of the pixel is also a human interpretation. Which pixel should be selected for the edge and not. Again, selected, we will do some operation crossover. That after crossover, we will take a mutation and it will be a totally new pixel. Again, when you do a genetic algorithm from a scratch image or a raw image without doing any pre-processing generation method, you come into a wrong edge, exactly wrong edge. When you try it out from your end, because the randomness is very high in genetic algorithm. The random nature is very high, because after crossover, the image intensity you are getting is totally different, because it will be only relating to the ones and zeros operation, AND operation or OR operation or NAND operation, whatever operation you are doing. It will be totally related to that. So you are getting an intensity value of an image of a totally different nature, which you cannot imagine also. If you have a 100 grayscale value, it will be represented in binary numbers. You have 120 grayscale value, which will be represented in a binary image. when you do an AND operation and OR operation, you will come across and come into a different value, which even, and we are doing this operation only bitwise, bitwise operation we are doing. And bitwise operation, if you are doing, you will come up across with a totally different grayscale value, which are not relevant to your problem also. So you come across totally different edge. So here the evolutionary methods of this kind of a new generation methods, we cannot suggest as a standalone. When you do it on a standalone image, even if you take an house pictures what you have seen initially, and you try a genetic algorithm from this starting part, you will get an image which are not at all an edge detected image, which are wrongly detected. And when you have a conventional method, on upon that, if you go a genetic algorithm, then you will have an advantage. So evolutionary methods, when you go for a standalone purpose, it may not suit. But you have a consistent method with you or a conventional method with you, then you apply on genetic algorithm or bacteria foraging algorithm, then it will be a good choice. The randomness is very high. We say that it is optimization. In some, like if you go for a biotechnology, DNA sequencing, something like that, the randomness may be following the universe rule, so that it may be suiting, and it will also optimize after a long time. Because in genetic algorithm, when you go for a simulation, you should know the starting result and the ending result. Then only you can validate. But when you take an image and you don't know the true edges for validation, that is an assumption. Or we have to manually draw the edges. That is also an assumption. So genetic algorithm will be better at starting the result and ending the end result you should know, and you converge to the end result in genetic algorithm. Randomness is very high when you do the kind of operation. In particularly in image processing down, because gradient value, logical operation may result in total disastrous way of edge detection. The standalone method, we cannot recommend the genetic algorithm method in your custom application. The particle swarm optimization, we can mock the flocking of birds, schooling of fish, and movement, everything we can do. And it's also a global optimization method. And we will be looking, we have a number of applications for particle swarm optimization. Here also, high rate of conversion, fewer operator, and each state have their own memory, they have better noise function and everything. Again, we will taking an example for particle swarm optimization as anti-quality optimization. This is one of the famous way, and I have given an example as sunspot. Basically, I worked on the solar images and solar images which you will be having sunspot, and we are detecting the boundary of the sunspot and all. So when you're looking at an anti-quality optimization, the foraging of fat, like bacteria, here also they are going for the food only, because the foraging in behavior is for food only. And the thing is that bacteria, we don't have a property called pheromone. But if the pheromone is there or not, we don't have a biological evidence for that. But when it comes to ants, when you are going for a detection, edge detection, what are things, the nature what we follow is like that. We will be going from nest to food and coming back, and it will take different paths, and the path will be retained only with higher pheromone rate. And pheromone is something called a chemical substance released by the ant when they move, and that will be deposited on the location they move, the geographic location they move, and it get evaporated. And when the ant move, and when the larger concentration of ant is moving in a particular direction, the pheromone concentration in that path will be higher. And the upcoming ants or the following ants can identify this pheromone concentration, and they can follow the path. Finally, they converge to an optimal path, and all other paths will be rejected. So that we have seen in the image. So this is the way the ant-colony optimization works. And again, our ants represent, when you go for an edge detection, ants represents the edge detector which goes on the image. And our image is the grayscale values of the pixel is our pheromone. When an edge detector starts forging on that, we will be identifying the gradient value, and the hands will be simulated in the image, and it will be moving across its gradient value. And the similar gradient value they will be taking as an edge, and they will be moving, and they will be putting pheroma. And pheroma, everything will be considered as an array of values. We will set a value of 20 of array 20, and each detector will move, and it will be decremented by one value. At last, when they reach food, it will become 0. Similarly, each individual ant will be considered as an individual array with a pheroma and of a location. It's like a pointer. Each ant will be considered as a pointer and moving across the image with a data structure having a pheroma matrix and a location matrix of this ant, and move across this nest to the food source. So same thing will be replicated in an edge rotation. Here also, when you take and standalone method for an ant colony optimization, again the problem comes, because the gradient value will be totally different in different locations. And when you put the initiate the ant in the different location, incorrectly we will also put the ant in the incorrect position of the pixel position of an image. It will force that location and consider as an edge where there not be an edge is there. So the forging of the ant should be given in a correct position. Then only the matrix representation of it, because each ant will be having a location coordinates and a pheromone matrix. It will be updated every move. It will be updated, and move is between the pixel, one pixel to the next pixel. In 8 neighborhood, it can move. In 8 neighborhood, it can move across different location, and it will reach the final destination. And here there is no food. Instead of food, the end of the image will be happening. Either vertically or horizontally, the edge of the image will happen. Okay, and also the nature of this hand and the pheroma they will be using for communication medium, because communicating between two ants. So that will take. And here the problem is that each ant will be providing a pheroma, and that pheroma should be referenced by the ant going in both directions. So all this, the complexity is very large, because the pheroma matrix of this ant will be communicated with the pheroma matrix of another ant, and these all the ant have their own location position, and this kind of things we can do easily in the parallel processing, which require higher amount of processing. Again, the standalone method, it may not be an ideal one. To start with creating an edge rotation. But what we can try it out is that we can try it out and like a region growing method or something like that. And in that method, when you try it out in ant colony optimization after the initial edge match, it may be better, because the edge which are not detected, incomplete edges, everything can be filled up, and you will get a better result. And these are the process how we will be moving. The algorithm is moving. Choose a seed pixel, and choosing a seed pixel is very important. And when you take and solve ant colony optimization as an edge rotation method, it may fail, because you choose a seed pixel based on your assumption, and it may not be the ideal choice pixel, seed pixel. So it is better to have a conventional method like gradient method will be there, and we have an addition to that we'll go for VCU. So that will become a hybrid way of approach, and it will go across the image and we'll get an ideal edge rotation protocol. Then comes another type of web viewing algorithm. The web viewing algorithm is or spider viewing web viewing algorithm. It's also an particle swarm optimization methods. Basically, it comes under the spider behavior, or we call it bio-inspired algorithms. The ant colony optimization is also bio-inspired. Particle swarm optimization, commonly looking at the fish, birds, and that kind of thing. When it comes to bio-inspired, we are and also web viewing algorithm spider. And exactly, the spider algorithm is commonly used in the communication network, not much used in the image processing domain. Where the communication network will be designed based on this web viewing algorithm, where there will be spiral locations will be there, and this spiral thing will be connected between some nodes. And how the network optimization is done, how to alternate nodes, when one some nodes fail, how the alternate nodes can be done. Particularly in the concept of the distributed computing. Later it become cloud computing or Hadoop implementation or Spark implementation, something like that. So the major role of the web aiming computer comes under this communication network or computer networks. But it is adopted in edge detection or image processing concept also, where there is a requirement we having a web aiming computer. Here becomes computer network basically the spider web weaving algorithm looking in a manner such a way that it is after the construction of the weaving algorithm we are implementing or we are simulating in the communication network. But when it comes to an image processing, the web weaving algorithm we will be starting. We are just starting the web weaving algorithm from the initial thread of the spider. And we will be start giving the entire environment and we will be segmenting our identity from that. So the spider will be moving in different directions in the web, and the entire web will be considered as an image, and it will be moving in different direction, and it will be fixing the silk. And here also we will be considering as fixing our edge replacement. And here also we can say that initial segmentation we can do a modified Canning method. And the modified Canning method talks about like we have 3 scales in the detection in modified Canning detection. So out of the 3 scale, 1 scale is not relevant. Scale of detection is not relevant. So we will neglect that and we will multiply after 2 scales. That is called the modified Canning method, which is later introduced in the detection literature. Initially, Canning method was actually not. Then they made a modification saying that the scale factors out of 3, 1 scale is not relevant. So just omit that scale, and you do the multiplication of the first and second scale, you will get a better result. So we commonly use Canning edge detection, and the modern edge detection method, the modified Canning method, is commonly used. When you take the initial segmentation from the modified Canning method, later you are implementing your web weaving algorithm. Then we will be having a hybrid method, more than hybrid method, not sake of using an hybrid method, but it will have a better result also. Because hybrid method may not be optimal in all the environment or all the research environment or problem. We are not using it as a sake of using, but we got a better results in the literature for using a hybrid method. Based on your requirement, you choose the conventional method along with an evolutionary method or a bioinstrument method, and we can create better edges and the end result or edge map which are optimized in the nature. Because commonly we will get an edge curve for every single method, edge detection method. But when you go for this kind of a combination, you got an optimized one, which are useful for your different applications. So that's how we can combine the Canning and the web weaving algorithm. Also, the end-colony optimization have a better combination with the region growing algorithm as the initial step, and we can connect it. And this is the way how the spider is doing this kind of segmentation. When you take an web weaving algorithm as a standalone approach, there will be construction of web is done, and that will be replicated in our edge detection method. The movement of spider and also will be, and this is the way the spider is moving across the algorithm and the step they are doing. They move across the edge map. If the disconnect path appears, then it's move for a 9 to 9 region based on the orientation of the direction forward and check the condition for connectedness. And if the connection match goes to the next step, otherwise stop the spider region. Move forward the web you connect the disconnected edges. Because here the main focus is for the disconnected edge. When you look at the ACO and for the spider web view, we are focusing for the disconnected edges. That is an optimization. That will be done accurately by the spider web weaving algorithm and end-colony optimization. rather than going from the scratch aggregation. Again comes another bioinspired algorithm. We call it as a whale optimization algorithm. Whale optimization algorithm means the approach the whale they are doing to for the prey. So they will do in a circular motion, and every time it will producing some bubbles. The prey, the small fishes of the prey will consider this as an boundary they should not cross, and they remain on that within the circular boundary. They will remain in the, and it will catch all the prey. So this is one of the optimization, and we call it as a bubble net hunting maneuver techniques of humpback whales, something like that. And this is also taken as a widely accepted technique to the aggregation method, and it's something similar to the spider web weaving algorithm, but the approach is something like that. It's an n-dimensional or three-dimensional way it is approaching. In spider web weaving algorithm, we have a two-dimensional approach. Here we have a third three-dimensional approach in which the movement is happening. And basically, this bioinspired algorithm also taken for the exploitation of the modern days aggregation algorithm. They also have a same type of a comparison with the aggregation and how it can be done. And there is no three-dimensional structures. But when you talk about the three-dimensional structures, when you go beyond because we are not only interested to for grayscale images. We look into an RGB image or an hyperspectral image or a CMYK image. Even CMYK image and RGB image of having less relevance to the whale optimization. But when you look at the GIS or the satellite image processing, where we have a hyperspectral data is there. When you go for an hyperspectral data, we consider as the prey is the entire cylindrical column. We will not think that the prey is at the top. We'll say the prey is at the cylindrical column all across the locations. Different locations they are like you consider this as a location. It is a prey is there, here the prey is there, and here we have another prey. Here we have another prey. And this kind of things will be there in across the entire cylindrical column. And when this kind of things happen, it will be simulating something like hyperspectral data of GIS, because in hyperspectral data of GIS, all the different band having different information, and all information we have to get, whether in between we have to find the edge or whatever thing, all the information is relevant, and we think it is a 3D environment. Hyperspectral data is any other 3D, and the aggregation is not solely dependent on a one band. It will be dependent on n bands. Whether it will be how many bands is there, it's relevant to the application what we are using. List 3 images or SAR images, synthetic aperture radar images, whatever may be, the different band contain different information about an edge or our region of interest is there. So when it comes to that kind of images, and also the RGB image, we have a three-dimensional perspective. When it comes to CMYK image, we have a four-dimensional perspective, where this kind of whale optimization have a better relevance to an aggregation environment. So this is the way we correlate with our bioinspired algorithm along with our image processing technique. And also numerous applications, what we call as communication network, other application also uses this kind of methodology in a better way, because the spider web weaving algorithm is optimally used in the network, computer network optimizations, rather than image processing. We cannot use this as a standalone operation in image processing, but in computer network it is used as a standalone operation. But when it comes to the whale optimization, the how it humpback prays, and this is the path they are following, the shrinking approach, the randomness approach. This approach can be also taken in an n dimension of the images what we have in hyperspectral data of satellites, or the 3 dimension of the RGB, or the 4 dimension of CMK images. Same thing we can correlate and map, and we can have this kind of agitation technique relevant to our application. And basically here also the food, the animals or the bioin's food animal is going for a food. All the cases the same thing happening, and also everything also the same thing happening. Hummingbird also they are taking a prey from fish from the water, and to have a stagnant, it will be flying and it will not maneuvering and it will be keeping in the same position. So that will be replicated in our helicopters, which Apache helicopters, which can take off and again in a position maneuvering something like that. They are taken. So these things are the replication what we are in the whale optimization algorithm. And this we can take in the acceleration also. Shrinking and circling prey, bubble net attack method, search for the prey, the exploration, everything we can have a representation in our acceleration also. So this I am concluding my part with. I think that will be an overview about we don't look at the equations or the demo of these all things because it's a recurrent processing part also. Starting from the conventional methods, classical methods, gradient methods, the Laplacian methods to some fuzzy and the neural network, which are the starting for the artificial intelligence. Then we go for the Bayes algorithm. And finally, we come to an hybrid method, saying that a combination of these methods, which are relevant to your application or your application domain or your problem domain, will be an ideal for your acceleration methods. So, if you're doing in a cloud, in a parallel processing environment, or in a remote way, it will be ideal for it. So, by just will be closing like research is farmers' curiosity, and everything is a curiosity. It's nothing like that. We have a defined way of doing things. Everything is a curiosity. We are poking and prying with a purpose, and we'll trying out new things. We wish that, or I wish everyone that will come across a new way of invention, or a new way of research methodology, or research outcome in the way of smart computing, or smart processing, or acceleration methods in the future. Let this FTP be an eye-opener for everyone to be a better prosperous in the research. Okay, thank you from my part. Any questions?
Thank you, sir. If you have any questions or queries, you may type in the chat box or you may unmute and ask.
I hope everything is clear. Thank you, sir, for joining us. We are really enlightened with your knowledge and presence. I request you all to fill the feedback form which has been provided in the chat box. Kindly fill it as soon as possible, as it will be open only for 30 minutes. Now we will have a break for half an hour. The next session is quite interesting, one on ML in software engineering, handled by Dr. C.K. Raju. The session will begin at 12, and please do join 5 minutes prior the session.
Yeah, there's one question. I think is there any researchers of edge computing in medical images? Yeah, medical images is one of the major applications. When you go for any real-time problem with medical images, one of the major area where acceleration is happening. And it is happening inside our MRI scan or CT scan or 4D slicing scan, everything acceleration is happening, and that acceleration algorithm is also patented with companies like GE, something like that, Philips. They have patented it. And if you are able to create an acceleration optimum for a 40 slicer scanning machine or our MRI images, then it's a great thing, because they have patented it and they are in their product, and it is automated. and it is not a way they are doing in an open environment. It's one of the great thing they are doing with this kind of MRI. We have seen the different scanning. We can go for any slice of our body parts, any number of slides we can get, and the major role players are GE and Philips in this environment. And that is one of the ideal example what we can see as and also we have a scanning. The scanning part is one of the major area where we can see the medical image processing is happening. And the agitation and segmentation is a major operation in that in the background operation in that imaging part.
Any more questions? I hope everything is clear. Once again, thank you, sir, for joining us.
Thank you everyone, and giving me an opportunity for the part of the STTP. Thank you for the management and principal head of the department, all the representation from the department, and being in the computer science and engineering, and also Dr. Anil K. Jacobs. Thank you.
Okay, thank you. The next section will begin at 12 and please do join 5 minutes prior to the session. Stay safe and thank you.
Shashi.
വണക്കം എങ്ങനെയുണ്ട് കേൾക്കണ്ടോ രാജു
Yes, yes. Am I audible? Yes, I think it's
Yeah,
okay.
very clear, very clear,
Oh, okay, thank you.
very clear. Okay, okay, Raju, relax.
Good afternoon, everyone. Welcome back to the second session of the day on machine learning in software engineering. We all know that machine learning is a study of computer algorithms that improve automatically through experience. To let you know more on about machine learning in software engineering, we have Dr. C.K. Raju, who has taken his BTech in CSE from GEC Thrissur, MS from BITS Pilani, and PhD from IIT Kharagpur. He was a former faculty member at MES College of Engineering, Kuttipuram. He has 22 years of teaching experience, 7 years of industry experience, and he is currently working at Madanapalli Institute of Technology and Science, Andhra Pradesh. Sir, it is our honor to have you with us today. Let me hand over the session to you, sir. Over to you.
Thank you, Ms. Sona. Firstly, I must thank Dr. Shashidharan for having invited me for this STTP organized by MES College of Engineering, and it's a great privilege to be speaking, discussing, arguing with most of my former colleagues and many of those who have joined this session. So with this brief introduction, let me get into my presentation. Okay. Okay, I hope the screen is visible now. Okay, so let me start. Visible?
Yes, sir. The screen is visible, sir.
Okay.
You may start.
Okay, thanks. At this point of time, I'll not be able to see any of you. Okay, so if you feel something absurd being coming out from my mic, okay, please feel free to stop
Yes,
me.
sir.
Okay?
Yes, sir.
Okay.
We will let you know.
Okay. So let me start straight away. Okay, so this is an STTP, okay, funded by AICTE, okay, and organized by MES College of Engineering. And today we are on the second day. And yesterday I was there listening to my HOD, Dr. Mahbub Basha, who was discussing about visualization techniques, okay, using pandas and Keras framework, okay. And he had also been using the Colab environment. Okay, so my discussion today will slightly be a continuation of where he has left yesterday. And today morning I was not fortunate to listen to Manish TI, okay, again my former colleague. And I guess edge computing, I don't know, there are many people who are saying many things about edge computing, but I guess largely, is it something to do with localization of data where it is needed so that you optimize on the communication cost? No idea. Okay. So I would have loved to listen to it. Okay. And another thing that Dr. Basha wanted me to ask is whether the recordings, I guess you are recording this session. So will the recordings be made available to him also? Is there a possibility, Dr. Shashi?
Yes, Raju, it's okay. It's okay. Everything is also available on YouTube.
Okay, fine. Thanks.
YouTube
Okay.
Live,
So
YouTube Live is also there. I can send to him now.
Okay, I'll convey that message to him. Okay. So with this small introduction, let me start. Okay, so machine learning in software engineering, that's a very difficult kind of subject, okay? Because software engineering talks about various methods in which software gets engineered, and machine learning is not that kind of a software and neither a finished product as such. Okay, so basically, what I'll be interested to discuss is how techniques in machine learning get propagated. Okay, so that will be an interesting area. Okay, and I'll let all of us. Okay, I'll not be giving any direct indication, but I'll be taking you to certain examples. Okay, and from the examples, it will be quite evident that these examples do not pertain to any of the known methods of published methods of software engineering. Okay. So that's a very interesting part. That will be an interesting part. Okay. And towards the end, I will discuss, maybe if we get time, we'll discuss about what was the software engineering that we were discussing these things about. Okay. And before I formally jump into the discussion, okay, I must first apologize for not getting a chance to meet all of you and ask what you would like to learn from us, okay, or discuss, because I am also, like many of us, a novice in machine learning and deep learning. Okay. So those things apart, I have made certain kind of a prediction, okay, assuming that most of us are new to this topic, okay, and that's where I am starting the discussion on. A couple of weeks ago, it should be in October, the Andrew Ng, who is now currently the co-founder of Coursera, Andrew Ng had floated a course on machine learning in Coursera at least a decade ago. So I participated in that, okay, completed that course. And a couple of months ago, he was again there discussing with some of the greats like Jan LeCun and a few other academicians also, mostly from American universities, about the prospects of machine learning and deep learning. Okay, and one opinion attracted me the most. Okay, and that was something like this: the professor from Stanford University commented that there is something called half-life, okay, for radioactive substances. Half-life is where the radioactivity, okay, causes the material to decay and transform into another substance, okay, altogether. So he said, relating, so we were thinking about how half-life and radioactive thing is related to machine learning. Then he finally said that after explaining all those concepts about, refreshing all those concepts about radioactive decay and half-life, he commented that many of the frameworks in machine learning and deep learning, he said for the first time, is also having this particular attribute of half-life. Okay? And he said that most of the frameworks that we discussed today will not be relevant a couple of years from now, okay? Because its half-life might have already, okay, caused it to decay beyond any resurrection. Okay, so now some new framework might have taken its place. Okay, and he says of most of the knowledge that is getting generated these days have got this particular attribute of half-life. And he said that AI, the frameworks which is used in AI and deep learning, okay, has got the maximum value. Okay, so it's the minimum value of radioactivity. Okay, which means it wears off, wanes away very fast than other frameworks. Okay, so it is with this comment of his that I would like to start my discussion. So, which means that the frameworks that we discussed today need not be so religiously followed, because a couple of years when we start actually jumping into it or diving into it and actually going with hands-on, okay, there might be new frameworks which have appeared on the horizon. Okay. Let me start. Okay, so why we are doing this is because now we have something known as an academic ecosystem landscape for us to follow, where we are supposed to be doing all these activities. So if we look at all these domains as boats, okay, sailing in an ocean, we are supposed to be putting all our hands and feet onto it and then taking it across. Okay, and as teachers, we have another role to us. We just cannot be practicing it. We also have to train another upcoming generation on how to do this circus. Okay. So with this, let's start. Okay. And why we are here is because there is also a peculiarity about this particular webinar. Like Dr. KP Mohammed, our former director, I think he's also current director. Okay. So Mohammed sir, I heard him echoing the sentiments, saying that the webinar is allowing many people to join this kind of conferences, which was not possible earlier. Okay, so despite all the major disruptions which are happening in other spheres of life, at least in the academic domain, okay, it is not happening. Okay, it is not taking shape because we are able to carry on. And this attribute is known as resilience. Okay, so we have a resilience. Okay, so the techniques that we are discussing today has a resilience to withstand many of the disruptions. Okay. With this, let's start. And why this disruption is because we are in a post-COVID era, okay, where COVID has started. So there are, when I say post-COVID, it doesn't have a hyphen between post and COVID. Okay. Similarly, there is a, which means there is something known as a pre-COVID era. So pre-COVID era is the era where the corona diseases were not there, and post-COVID is the era where corona diseases are there. Okay, so it is already here. So we are in the post-COVID. Now, if there is a hyphen coming in between post and COVID, it is a post-COVID era, which means COVID era, the post-COVID. Okay, post-COVID era has started, but the COVID diseases has ended, and we are out of the COVID phase. Okay, so that's the meaning when there is a hyphen in between. That would be an era where COVID is no longer there. Again, after COVID has started. Okay, so these are some of the implications of words. And we are here because there is a rise in number of corona cases. Okay, so if you look at the graph, we find Maharashtra and Kerala, South Indian states. Okay, looking at this state, not a very pleasing sign. Okay, so it's not a pleasant figure also. So we are concerned, and we are all eagerly looking at these graphs to come down and touch the x-axis. Okay. So this is my topic, machine learning in software engineering. Okay, and one of the concepts of software engineering is to make assumptions about certain models. Okay, so here, as I told you, hinted earlier, there won't be any particular model that I'll be discussing, but at the same time, we'll be indulging in certain kind of activities which will resemble a new model. Okay, so it's for us to take note of what kind of model is this, okay, or to which existing model of software engineering does this closely resemble to. Okay. The third aspect that I would like to highlight, okay, is that yesterday when I was listening to Dr. Basha, I was in Kerala. Today I'm in Andhra Pradesh. Okay, so I've been traveling all the night. So there's a possibility that I might fall asleep. Okay, usually some of the audience, I am good at putting audience to sleep. Okay, so this time it's the reverse that then happened. So if you don't find my voice, if you find silence, okay, I request you to alert Dr. Shashidharan, because some of my colleagues who might be having my number, and ask them to wake me up. Okay, so let's start. So as Sona introduced, yes, any comments? Okay, so as Sona explained, what is AI about? It's the ability to learn from experience. Okay, so if you have something where we have configured a machine which can learn from experience, we say it is AI enabled. Okay. And what is machine learning? Okay, so let's look at the typical programming paradigm that we are exposed to. Is if you have got a problem, okay, say suppose we have to find an average of certain numbers that are given to us. Those numbers become the data, and the rules for generating the average are something that we call as algorithm, and then we'll feed it into we'll also use a programming language like C or Java or Python or whatever. Okay. And then we'll do the programming part. We'll generate a flowchart, and then we'll fix the convert the algorithm to the programming language, and then feed the language with generate the binary output, and then feed the output with this data, and then we'll get an output. So this is the conventional paradigm that we are used to. But in machine learning, it's some of these have been turned upside down. Okay, so instead of output coming at the right side, you are now feeding the data with the output, which means you're providing answers with the data. Okay, and then you are expecting the model to push out certain rules. Okay, so at the end of this exercise, what retaining will be a machine learned model, okay, which knows the rules under which the data is mapped to the output. So this is the fundamental paradigm change that has happened with the machine learning when we compare to the conventional learning models. Okay. Now, why this has happened so far and why we are discussing it today? In fact, across the world, everywhere, machine learning and deep learning and many other aspects related to artificial intelligence are being discussed. And why it has happened now and why did not it happen a couple of decades ago is because of these 5 factors which are shown here. Okay, one is abundance of data, both the structured and unstructured. Okay, so earlier we didn't have so much of data. Today, because we are networked, we have plenty of data. Like this particular discussion is on YouTube, so you have a large number of YouTube videos. We have a large number of social networking sites and tools, okay, which continuously keep generating data, and all of these are available to us also. Most of these, okay. We have most of the news portals coming up which are archiving their news, okay. So somehow the storage value, the cost of storage has reduced, okay. The means of storage have increased, and there is an abundance of data. And not just this, there are also data sets which are available to us now, which are sort of a kind of cleaned data, okay, archived in certain formats that we are ready for use, okay. So we say it is over-the-shelf data, okay, OTS data, which we can readily pull out from the shelf and push it into our program and then use it straight away. Okay. Though that is one aspect. The second aspect is the growth of hardware. Okay, so even today's smartphones, but a couple of WhatsApp messages that most of us have received in the past say that even Apollo 11's space shuttle's complexity, okay, is less than the complexity of the hardware that we have in our mobile phones. So most of the school students these days have computers, some kind of a digital equipment in their hands, which are more sophisticated than those things that were there some couple of decades ago, like in the 70s or 80s. There is really an explosion of hardware. Okay, Moore's law still continues to hold. Okay. Then third is presence of a community. It's not just one community, there are communities of communities getting together. Okay. For every issue, there is a community discussing it, who are interested in it, and there are plenty of communities which are generating the software and the libraries and programming languages, so that and even getting together, they are doing the coding also, and they are sharing the code also. So it's a huge repository which is building up very recently. Okay, this is a phenomenon which is happening, particularly taking shape in the last couple of decades. And this is where software engineers, the software engineering discipline, okay, has to take note of, where you have plenty of code which can be used and reused. Okay, all those things, okay, even the techniques, okay, can be reused straight away. Okay. And that is one thing that will be that I'll be demonstrating today, how to make use of an existing code. So I will not be taking the way that Dr. Basha took yesterday, where he took the pains of doing the coding. I'll be pulling out the code, okay, which is shared by somebody else. Okay. So why in fact, Dr. Basha is an excellent teacher. In fact, most of the good teachers would like to do it that way. Okay. But there are people, okay, but there is a limit, there will be a limit if I do that for large pieces of code, okay. It will be very difficult to complete the coding exercise, okay, in that short framework. Whereas if you pull and allow certain black boxes, okay, so which means when we pull somebody else's work which is not documented, it might appear as a black box to us. So we'll try to pull out certain codes, and we'll work with these black boxes, okay, and then slowly try to see whether we can unravel what those black boxes are. Okay. And the fourth one is availability of tools. As I just mentioned, there are not just communities, hardware and data. There are also plenty of tools which are being circulated, okay, and most of them are free and open source as well, which means we have the freedom to not just to use it. Other proprietary software will allow us to use it only. But for a free software, we not only can use it, we can also tinker with it, we can extend it, and we can even make an extension and publish it, publish the extended one. And the important aspect is we don't have to ask permission from anyone to do this. Okay, so that's the biggest advantage of free and open source software tools. Okay, and the last one is investment. Even governments and companies and corporates, okay, have pulled in huge amount of money into this. Okay, and with all this, when all these factors have started working together, we have what is known as the peak. We are at the peak of the hype cycle. Okay, where it is not only the language, the environment which is getting perfected, the expectations are also getting increased. Okay. And combined with this, okay, so when you have all these factors coming up together, what we'll have is, intelligent people, institutions will all get their act together, and they will start working on application domains. So we have certain domains which are coming up. Okay, so let's look at each of those, and these are very familiar to most of us. Face recognition. If we, for example, if we upload a face, somebody's face onto Facebook, it will immediately ask us this question, whether we would like to tag Mr. X or Miss Y, which means Facebook already has an application framework running at the back, a learning and intelligent framework running at the back end, which has recognized this particular photo. And the second is image classification. In fact, it could be image classification, it could be object classification, it could be anything. Okay. If you look at the Google Lens, the application which is there, okay, with the kids, okay. So if we found an insect which is not in our vocabulary, okay, which we have never come across in the past, we would be scared to go near it. But our kids are not the same. They will point the phone onto that insect, turn on the Google Lens, and take a snap and ask to Google what is it, and it will tell them all the classes to which this insect is likely to belong to. Okay, so there is a rich taxonomy of not only insects and plants, okay, of almost all the objects which are there. Okay, and there are also applications which is helping us to do this. So that's the kind of domain of image classification. It's not just that; it has gone even further. In fact, you have even autonomous vehicles coming on, which will read the signboards and which are coming there on the roads, and infer the meaning out of it. Okay, so if anything is written there, it will try to extract the text from that particular object, okay, and take action accordingly. Okay. We have speech recognition, okay, and if you have observed, I don't know whether you have observed this or not, on an Android phone, if you are talking to somebody and if you ever happen to utter, it could be a phone call, and if you ever happen to utter a name of an interesting thing, okay, or event, the next thing that you'll find it is that in your Facebook or WhatsApp, okay, or in some Google related applications, and advertise related to that particular event or object that you have discussed just recently with your friend, but not put anything on black and white in your screen or anywhere, might pop up, and you will be surprised to know how come. Okay, you are searching for this necklace, and then suddenly you have a necklace coming on your mobile phone. Okay. So that's the kind of world that we are living. So that what that means is that there is also a speech recognition software which is running on our phone. Okay, so Android phones, which is released by the consortium on which Google also is a member. Okay, the consortium has allowed this kind of an application to get integrated to your phone. Okay, which does all these kind of things. Okay. Now that might be irritating to some of us, okay, because it might distract us from what we are thinking. But for young kids and for the corporates who are promoting this that activity, for them it's a boom time. Okay, for the corporates it's a boom time, and for our kids, young kids, okay, kids who are not so alert to it, okay, they might be seduced or induced to, to take further action based on what they've seen or heard. Okay. The fourth is text to speech. Okay, so you write something and it gets converted to speech. Okay, so for blind people, there are large number of applications today where even PDF files or newspapers, okay, can be read from source. So what it does is it converts the PDF image to text at the first level, and at the second level, that same text is rendered to speech, okay, using a speech generators. So that is there. And other applications is if you have been to airports or railway stations these days, and if you can recall the kind of messages that were there a couple of decades ago, or we'll find that those days when the message of a train arriving there will be at least 4 or 5 different tones for the associated with each patches. Okay. So it will not be a continuous, it will not look like a human being rendering it. It will be clear to us that it's a machine which has recorded in these texts and words into as parts, and they are just assembling it and then putting it out on the speakers. Okay. So that's not the case today. Today these are as if a human being, okay, is making a comment. Okay, so there will be proper punctuation and proper gap is maintained. Okay, so all those rules about natural languages will be followed when it is converting the text to speech. Okay. The fifth one that we have shown here is handwriting. Okay, if most of us have been using WhatsApp, okay, or any other application for that matter, people generally use most of the handwriting transcription in WhatsApp applications, where if you want to have your local language get to be printed, okay, typing it out from a keyboard is a very difficult task. So again, the consortium has come out with an AI-enabled handwriting transcription mechanism, which is again a machine learning application which takes note of, okay, which learns your handwriting and tries to predict the results. Okay. The next is the language translation. So today the Google has its own translation page where, in fact, very recently AICTE has announced certain funding. Okay, government MHRD has announced an ambitious project of teaching professional courses in mother tongue. Okay, there are a lot of criticism to it also, whether it is possible, feasible. Okay, so those things apart, it's a very simple task, and they have assigned something like 1 lakh per publication or something. Okay, it's an easy way to make money. They didn't know that there is something called as Google translators, which are already there. So if it's a PDF file, you just convert the PDF file into text. Okay, cut and paste there, and then you look at the final language, select the language, final destination language, and then click the button, and then voila, okay, everything will be there in your local mother tongue. All you have to do is just check whether it is correct or not, and do a slight amount of override onto it. So that's easy. Okay, it's a click of a button plus a little bit of exercise, and AICTE is ready to fund. Okay, so that's an easy way for, if you have spouses sitting idle at home, maybe we can assign this task to them. Okay, so they will also start earning certain money. Okay, the next is medical diagnosis. So medical diagnosis is an area which has exploded in the last couple of years, where deep learning applications, there are many in this companies which are producing medical devices which are intelligent these days. Siemens is already there. Okay, GE Medical is there, and IIIT Hyderabad has come out with certain apps, okay, which can take a photograph of the retina of a human being. That means I can focus my own camera using that app onto my retina, and it will tell me whether I am affected with diabetes or not. Okay, so those kind of applications are already coming up on screen. So where it's a non-invasive in the sense there is no needle which is getting inside our skin. Okay, So it's a non-invasive. All it is taking is a photograph of a retina. And then based on the retinal images and the trained model, which is already there, it will predict what all diseases we are having or we are likely to have. Okay, so that's a major advantage. Big boost to the research which is going on in the medical learning. Okay. The next is self-driving automobiles. Okay, we have heard about autonomous vehicles. Okay, we have been hearing for a long time. Many Western countries have already started floating these machines, putting these machines on roads. Google has been doing this. It might, maybe, I do not know, but there are people who say that it might still take more time to come, okay, to materialize. But that is again one area where people are trying to develop applications which thrive on machine learning. Next is digital assistants. If we ever enter certain insurance website, okay, there might be certain assistants which will pop up, okay, asking us questions. And one WhatsApp meme that I observed is that for Microsoft, a certain thing comes up and it asks questions in such a manner that we will be fooled to think that it will have an answer for it. But at the end, it says, no, I do not have any particular answer to your problem. Okay. So those kind of things has already started coming up. So digital assistants are there, which will help a novice, okay, to gain some of the information which it needs to process, okay, and this processed information will be given to the representative, who can then finally come out with a firm solution. Okay. Then we have ads, recommendations, okay, search tools, and then whatnot, spam filters, many other things which is coming on, which are things based on, okay, certain applications which are based on our habits, okay, or on patterns which are already there in certain part of the text or something. Okay. And based on those things, they take an action, okay. And then for ads, okay, they look at in the initial part I told you, if you ever happen to say some words, okay, out of and which are captured by the system, okay. How much time do we have? We have time till 1:30, isn't it? How much time? First session?
Yeah,
12 to 1:30, isn't it?
Yes. Yes.
Okay,
Yes, sir.
fine.
Yes, sir.
Okay, fine. Okay. So those things are okay. So those things are there, and there's also criticism about these kind of recommendation systems, and which is getting noticed these days, and that is that if you start recommending a product, okay, a particular product to a person who is searching for it, okay, you are actually depriving the person from exploring other options, okay. So for the market, this is not a healthy sign. For the product, which has successfully been advertised, it may be good, but it may be good for the actual jeweler. Okay, if you are planning to buy a jewelry from a jeweler, for the jeweler, if it may be good, for the jewel industry, it may not be a good thing, because the other manufacturers will not be known to the person who is exploring it. Okay, so that will cause a negative effect on the markets, and markets may shrink, or something damaging might happen to the markets, okay, if these applications explode and succeed in their tactics. Okay, so this is a criticism that I have observed coming as it is from some research institutions in Europe. Okay. The next is entertainment. Okay, there are deep learning applications which will mimic, okay, and produce the voice and images and videos as if they were more real than real. Okay, so you already have Barack Obama. You can have Barack Obama talking about something. Okay, and you can also have, so they are also known as a deep fake application. Okay? So those things are also already there, and there are also images which are coming up. There are films which are coming up with virtual characters, and these virtual characters are more, okay, given the precise attributes that the audience would like to have. Okay, So you might have more beautiful or villains who are more, villain, who have villain faces kind of thing, which are nowhere near to any of the existing people around. Okay. So that's a whole industry which is taking shape now, and in a couple of decades, it might, first, I think it has already hit the markets. It might be very popular in coming decades. Okay, so these are some of the applications that have exploded on the scene. Okay, or have the potential to take it further. But the important part is, so where do we stand? Okay, so many research institutions says that, okay, so all these applications that we have seen here, okay, uh, uh, there is still space because some of the real pertinent questions haven't been formulated as yet. So it's up to us to formulate those pertinent questions. Okay, look at real issues that people are really concerned about. Okay, and it's for us to use these frameworks, languages, techniques, okay, tools and communities, and then try to solve it. Okay, so we don't have to worry, say, seeing all these things, okay, saturate, and some research institute might already say that, no, this domain is saturated and that domain is saturated and deep learning is already saturated and image processing. So for people who are willing to, going for a research program, they might get confused, okay, thinking where to, which domain should I be looking at? Okay, so we don't have to worry too much because the pertinent questions haven't been asked. So we just have to keep this in mind. Now, okay, so that's the first part. So are there any thing to add by anyone, or are there any criticisms on the first part that we have discussed so far?
If anyone have any queries, you may please ask now.
That's very good. So it means two things are likely to happen here. Okay, one is many people, okay, who are here are able to understand, okay, what is being discussed, or okay, nothing is being followed. Okay, or okay, is something irrelevant are being discussed here. Okay, so as a teacher, I would like to prefer, okay, as a teacher, I would like to think, okay, that it has been followed and understood, so that I will be happy. Okay,
Thank you,
let's
sir.
move
Thank
on.
you for your. Hello.
Okay.
Yes, sir. Thank you, sir. Thank you for your informative session, sir. The feedback link is provided in the chat box, everyone.
No, I haven't completed. Oh, okay. So was it Sona? No,
Yes, sir.
okay. It's not completed. There are 6 parts to it. Okay. So part
Yes,
2,
sir. Yes, sir.
the 3 parts will be covered in the first session. Okay. So let me continue. Okay.
Yes, sir. Sure.
Okay. Now we'll jump into a classification problem straight away. Okay. So let's look at this. So there is, when we are talking about patterns, okay, basically, okay, when we are discussing machine learning or deep learning, we are essentially trying to see whether we can train a machine to identify patterns. Okay. So let's assume this is the pattern. Okay. The figure 1 shows some white dots and some black dots, okay, on the screen, and then we are asked to develop a model for this. Okay, so how do we develop a model which can segregate the pattern? Okay, and in the next adjoining block, it says that, okay, if you draw a line, okay, drawing of a line is possible, segregating the white and black dots. Okay, and that line, okay, so that equation for a line will essentially become our model. Okay. So which means all that we need to generate a model is to frame the equation for the line, and after the equation is formulated, we don't need this white and black dots anymore. Okay, because if you are given some unseen data, okay, and we are asked to figure out whether our model will be able to distinguish whether that particular coordinates belong to the white dot or black dot, just by looking at the equation and looking at which side of this equation the dot falls into, we'll be able to come out with a prediction and say that it is more likely to be a black dot or it is more likely to be a white dot. Okay. So that's the definition of a model, simplest of model. Okay. And here if we can transform this the equation in such a manner that the whole patterns of dots are transformed here, and then if we can draw this, okay, then we know that anything, okay, where x is positive, x is a positive value, will be black dots, and any coordinates where x value of x is negative is a white dot. Okay, so if you are able to transform this particular image, okay, these dots, and do a certain bit of homework, extra work by transforming it, then we'll be able to come out with a more simpler, okay, a model. So that's the idea behind classification. Okay, very simple idea, and most of the things that we see here are all extensions of this. Okay, so let's move on. So let's move on with another pattern. Okay, so this is a pattern of the image on top is a pattern which represents, okay, from our brain we can say that it is 5. Okay, and we are asked to develop a neural network which will predict, okay, this particular figure as 5. Okay, and what it says is that for this to happen, if you are in the traditional programming environment, we would have to write plenty of lines of code, because we have to take into consideration all possible combinations where a handwritten 5 can appear. Okay, so you will have to make millions of people write 5, and then try to write a code, which will find out the unique distinction, and say be able to come out with a prediction and say that it is most likely to be 5. But in machine learning and deep learning, what is important is, particularly in deep learning, what is important is that it takes only 6 lines of code for this prediction to happen. Okay, so all that we are supposed to recall is just 6 lines, and these 6 lines will be repeated in many of the programs as well. So we don't have to actually remember also. Okay, so this is a peculiar feature of software engineering. Yesterday, Basha sir was taking all the pains to write those codes. So let's see, without making any, let's pull out somebody else's code and try to see what it is. So this is a code which is coming here. Okay, so on the left side you will find 6 blocks written, and these are 6 parts to it. Okay, and this is all what is needed to train, okay, develop a neural model which will be competent enough to predict, okay, the input features, okay, looking at the input images, and make a prediction based on the model that it has been perfected. Okay, so let's look at the feature. I hope this image is clear. Okay, so let's look at this. So there are 2 parts which are very important here. Okay, I'll not go into the other parts. Let's assume all those things are black boxes. Okay, unlike Dr. Basha's strategy. So let's make certain assumptions wherever they are. Okay, so we are assuming all these are black boxes, and that this is a model which predicts, okay, some handwritten codes. So let's look at this. Let's look at some of the important part here. Okay, so here we have given the input shape. Okay, something shown as input shape and being reflected. The parameters are 28, 28, and at the bottom part we are shown as 10. Okay, so this is the input part, and this is the output part. So what it takes is, what it actually does is, it takes an image whose dimensions are 28 pixel by 28 pixel, okay, and then makes a prediction, okay, to which of these 10 digits it belong to. Okay, and these 10 digits are those ranging from 0 to 9. Okay, so for instance, if it is 4, which is coming here, if it is this kind of image, okay, the model should predict if it is if it is a good model, it should be reasonably good at predicting it as 4. Okay, so that's the 2 important part, and in the between, okay, you find something as 128. Okay, and that is the hidden layer. Okay, so here it's a single hidden layer. So you have 1 input layer, 1 output layer, and 1 hidden layer, and the hidden layer contains 128 neurons, okay, nodes. Okay, now let's again, okay, assume this to be a black box. We just as of now we do not know what is a neuron or what is a hidden layer. But just assume that there are 3 layers for this particular model. The first layer accepts the image, which is say 28 by 28 pixel. Okay. So, and the last layer is a prediction. Okay. It's a single layer containing 10 different values. Okay. Of which one value will be activated. Okay. Based on the model, based on the model computation that goes inside the model. Okay. Now let's look at this. Okay, assuming we have more than one hidden layer. So layer 1, layer 2, layer 3, layer 4. Let's assume these are all hidden layers. Okay. So what this particular model, this is another model which is being shown here. What it actually does is it creates 3 additional layers to the model that we are seeing here. Okay. So the number of lines for this code is not going to increase. It will still remain 6 because all that we are doing is adding more layers here. So we'll be adding 3 more layers here. Okay. But since this is a single statement, okay, the number of lines is not going to make any difference. It will still be 6. Okay. So adding more layers doesn't mean that the size of the program, okay, in the lines of a code is going to increase. Okay, they remain the same. So that's the good part of it. Okay. Now, what are these representations and what is the significance of these layers? Okay, so let's look at this. At the end of, let's assume, so these are the black boxes that we are slowly trying to unravel, and this is, and before I get inside, these discussions, okay, continue with the discussions, I must make a confession here that none of these slides are mine. These are taken from various public portals and stuff like Wikipedia, and I have not been given due credit also. Okay, not given credit to them because if I were to give credit, I would have to give credit on every single slide. Okay, so since none of these slides are mine, I thought no, why make an unnecessary statement here. At the end, all that I have to do is make out a single statement and say that none of the slides are mine. Okay. So this is an interpretation by one such author, and it is just to make things simpler to us. Okay, it may not be the correct one also. Okay, but let's assume that between 2 layers, okay, we will be able to reconstruct some image. Okay, some kind of an image, a transformed image based on the input one, and let's assume some features of this image come out in the first layer and the representation between the first and second layer. Okay, and similarly at after each of those layers, okay, let's assume that some additional features comes out. Okay, and towards the end we have certain kind of features which are coming up, which will be actually used, okay, to make this kind of prediction, and may say that it is most likely to be 4. Okay. So this is the neural model that we are discussing about, and let's look at this code and try to see whether we can try out one such code, program it. Okay, so let's go into the programming mode. Okay, so I am invoking Bhashar's style. Okay. So let's look at this. So this is a GitHub portal, and GitHub is a place where actions are all happening. And GitHub is currently owned by Microsoft. Okay, so there is another fork which has come out, which is GitLab. So many people have ported all their software there. Okay, even I have also ported all my codes, so that's GitLab also, because you do not know, you cannot predict what Microsoft is going to do with this kind of portals. Okay, whether it will remain free or not. So many agencies have forked it and created a parallel. So instead of GitHub, if you have gitlab.com, okay, it's the same. Okay, and most of the interfaces are already there. Okay, so let's assume, okay, continue with GitHub. So this is my login is CKRAJU. Okay, so this is my portal, and this is where /MESC is where I have uploaded, okay, shared the code, okay, for our experience today. Okay, and again, I must again confess that none of these codes are mine. Okay, they are again forked from somebody else's. Okay, so these are all coded by somebody else, and I just taken it, pulled out certain codes from somewhere, and I pushed it out, tested it, and then I created a repository. Okay. Now, assuming this to be there. Now, what if we find a new GitHub repository? Suppose you are looking at GitHub and you find you want to search for some deep learning, okay, solutions, okay, on Keras. Okay, it will provide you with large number of repositories. Okay, so let's assume you are there, you are looking at the first one. Let's assume this is the most important one. So you look at the number of forks. Okay, number of forks are number of people or institutions or organizations which have pulled out this particular code and have created a fork of it. So here it is 4,800 institutions which have pulled out the code pertaining to deep learning Coursera. Okay. So all you have to do is after creating an account, you have to press this button fork here. Okay. So if you have signed in, so this is my signing in. I am signing in. Okay. So here it will ask for verification. After verification, okay. Any comments? Okay. So after verification, all that you do is press that fork button, and then we'll find the entire branch coming up and settling in our account. Okay. So we'll be given a copy of it, and we can work on it. We can save. Okay. So we don't have to take permission from the other one. All that we do here is not going to affect the main repository. Okay. It is a local repository purely for our experiment purpose. Okay. So let's assume this is there. Now let us pull down this code into our desktop, okay, and try to execute in our desktop. Okay. So here I have used the software called Jupyter Notebook. Okay. Jupyter Notebook, and this is a Linux box. So if anybody would like to install it, they can go by pip install, okay, Jupyter Notebook, and it will install it. Okay. Otherwise, there is also a Conda. Okay, you can Conda install Jupyter Notebook. Will also install the software application. Okay, there is also a binary package available which you can download and install. So there are various ways of installing Jupyter Notebook. Okay. Best way is to again go for a Google and how to install Jupyter Notebook in Windows or Linux or whatever. Okay, we'll give you the solutions on how to install it on a machine. Okay. Now my aim is to create first. So I have put out a code in GitHub. Okay, so I have to make a clone of it on my local machine. Is somebody saying something? Okay. So let me pull out here. So I am making a Git clone of it. Okay, I am pulling out a clone of it. STTPS. Okay, github.com, CK and MESC. Okay. I'm pulling out a code from it. Okay, cloning into MESC. Okay, so it is downloading it, unpack it. Okay, so I'll have a directory called MESC now sitting here. Okay, so this is a directory. So let me go here. Okay, so I have created. Okay, so all this code have arrived at my desktop. Okay, from GitHub portal, it is now sitting in my desktop. Now let me execute the program. Okay, so I'll invoke Jupyter Notebook. So the application is a browser application. You don't need to have any other interfaces for it. Okay, so here it comes up. And let's try to run it. Okay. Okay. Now, yesterday, Bashar was typing it out on his own. Okay. So today we have all these cells here, which are coming from the program, which is already there on GitHub. Okay. So we don't have to write anything, but if you have attended yesterday's class, we know what this means. Okay. So it is importing the dataset from Keras library, dataset library. And that data is loaded into two sets, which consists of one part of training images and the other is test images. Okay, and then let's execute this. So we are executing this by making it run. Okay, executing. Once the figure a number comes here, it means it has been executed. Okay. Star means it is still downloading the data set. Okay. So Keras framework has got certain built-in data sets. Now what it is doing is it is downloading the MNIST, and MNIST is the data set which contains the 28 by 28 images, which are actually, okay, which is actually the first application to have made use of the machine learning. Okay, it's archived in it was developed for the United States Postal Department, where they wanted to sort the letters based on the zip code which is there on the envelopes. Okay. So it is downloaded now. Let's execute the second one. So we'll know the shape. The shape is 28 by 28, and there are 60,000 images of it. Okay. So 60,000 images containing, okay, say 6,000 images of 0, 6,000 images of 1, and so on, and 6,000 images of 9. Okay, so totally you have 60,000 images of handwritten codes. Okay. The length of labels, okay, should be 60,000. Yes. Okay, now the shape, okay, it is for the test one. So we have 60,000 training images and 10,000 test images. So that's the division here. Okay. Then let us look at what are those labels, sample labels. Okay, so 1,000 labels. They are now. So the first of the image represents 7, and the last image represents 6. Okay, that's the collection here. So this is a set of labeled images. Okay. Now let us proceed. Okay, empty set. Now we are importing the libraries. Okay, and this is the one that we saw there. Okay, let's say execute this. What it has done is it's again a black box. Okay, so it is taking all the input images whose dimensions are 28 by 28 and using them to predict. Okay, give a value between 0 and 1 onto the final layers. Okay, so the cell which takes the value of 1 is more likely to be the image which has been given as input here. Okay, and on the hidden layer we have 512 nodes for this. Okay, now let's look at our network summary. What is the style of this network? Okay, it will tell us that we have a dense hidden layer containing 28 into 28 into, so 28 into 28 is it is 784. Okay, plus 1 which is for accommodating your bias. Okay, so that becomes 785 into 512 means it is 4 lakh, okay, 1920, okay, trainable parameters in layer 1. Okay, and in the after the second one you have 5013, that is 512 nodes are there in the middle layer, hidden layer. Okay, you add 1 to it, which is the bias there. Okay, so it becomes 513. Multiply it by number of the output nodes. Okay, so you have 513 into 10, 5130 again trainable parameters. So these are the parameters which are supposed to be trained here for, and these are the parameters. So we have a total of this many 40,000, sorry, 4,07,050 trainable parameters in this particular model, and these are also weights, known as weights. So if we have these weights adjusted correctly, then we say that in this particular model, okay, we have trained 44,07,050 parameters, so that the model can now make a prediction on these images on which it has been trained. Okay, so let's look at this again, a black box so far. Okay, so we do not know what's an optimizer and loss. Okay, we'll discuss this in the later parts. Okay, so but as of now, let's assume that there is something known as a ground truth. Okay, which is actually the value of the image that is being fed onto it. Okay, so if it is a value, if it's an image pertaining to 4, okay, the output should have a sequence of values between 0 and 1 for all the nodes here. Okay. So against 4, the output will be 1, and all other nodes it will be 0 here. Okay. So the law says that when it makes a prediction, okay, if for a correct prediction, the ground truth is the one which shows the value against 4 as 1. Okay. And when it is doing a prediction, okay, it might predict it as wrongly as 5. Okay. So which means instead of 4 having 1, we are having 4's value, the predicted value of 4 as 0, and predicted the ground truth of value for 5 is supposed to be 0 because it is not 5, but the predicted value is 5, so it shows a value of 1 against 5. Okay, so there, if we look at the difference between these two, take the absolute difference, we find that there is a difference of 2 between the set of values, sum of the set of values of these two. Okay. Will be because in case of 4 there is a difference of 1. In case of 5 again there is a difference of 1, and this is an error. Okay, so loss is something which is a function which will apply a value to that particular wrong prediction. Okay, so if the prediction is correct, the value of the loss value will be 0. If the loss value is higher, it means no, the prediction has gone wrong. Okay, and the optimizer is the function, another function, which will again optimize the parameters or weights. Okay, with an objective of reducing the loss. Okay, so the optimizer's function is to make the loss value closer to 0. Okay, for which it will try to adjust the weights. Okay, and matrix is the one which will be used to capture, okay, the accuracy. Okay, how correct we were. Okay, what percentage of correctness was there after the iteration. Okay, so these are the three particular parameters in this particular compile instruction here. Okay, let's proceed. Again, still black box, but let's see. Okay, let's proceed. Now we are going to, okay, now here what we are trying to do is we are going to reshape it, and when we are reshaping it, the 28 by 28 pixels will no longer, it's a square matrix. Okay, so it will be arranged in a linear format. Okay, so it is reshaped, and then what we do here in the next step is we are dividing it by 255. Okay, so all values, and here the if you look at the input shape of the figure that we are giving here, okay, it is 28 by 28, and there is no third parameter, which means there is only one channel, so it's most likely to be a grayscale image. Okay, having 28 by 28. Okay, so black and white image. Okay, and that has been, and its value is 28 by 28. There are 784 such pixel values, and each of those pixel values are likely to have a value between 0 and 255. So which means that if it is a totally dark image, all the values will be 0. If all the pixels values are white, all the values are likely to be 255. And we know that when it represents a character, okay, some of the pixels will be having a value of 0, and some of the values will be having a pixel value 255. Okay, some might be even somewhere in between. Okay, so if we divide each of those values by 255, what we get is each value whose range will be between 0 and 1. Okay, it's a positive value, its range will be between 0 and 1. Okay, so all 255s will have a value of 1, all zeros will have a value of 0, and anything which will have a fraction value, real value. Okay. So that particular exercise is known as normalization part, normalizing. Okay, so we call it as a feature normalizing exercise, where we are normalizing the value, okay, to fall into a particular range. Okay, so for ease of computation. Okay. Again, we do the same thing for test sets. Okay. Now let us execute the next cell. Okay. Sorry, this didn't execute. Executed. executed. Okay. Now we are going to fit in. Okay. Now the training has started. Okay. What is this? So there is an error here. Batch size. Firefox. Okay. Let's run this once again. Again error. Got fit. We are running to an. Okay. So this is. So this is one danger of copying code from somewhere. Okay, so we might encounter errors. Okay, so it has started. Okay, so somewhere in the sequence got executed. Okay, so the values of training images and labels got mixed up. So that could be the reason. Okay, so it is now training. Okay, so the training is going on and it is adjusting the weights every time. It is comparing. So both the functions, the loss function as well as the optimizer are at work, and it is now predicting. Okay, 99.12% accuracy for the training data. Okay, okay, so for the test one, so we have at the end of 5th iteration we have achieved 99.12% accuracy for the training data, and for unseen test data, when it was fed, it gave us an accuracy of 97.60. Okay, so that's our model. So our model for unseen data. Okay, so it means, what this means is that if you are giving 1,000 images, we are likely to have this model predict at least 976 images correctly. Okay, so this is just a wild guess. Okay, but it may not be the same if you repeat the exercise, because because of various reasons. One is that the model, when it starts, okay, it might assume certain values for the initial values for weights. Okay. And if there is a possibility that the weights might differ and these values might also get changed. So there's no fixed notion for this. For this particular model and this particular iteration that we have done, okay, we have generated, our model has generated, all that we can say is our model has generated 99.12% accuracy for training data and 97.6 for the test data. Okay. So this is our first experiment that we have done here. So what all have we? So I'll just okay, go back and go back. How much time do we have now? We still have. Okay, still there is 20 minutes to go. Good. Okay, so we at this end, what you're seeing is we have downloaded an image. What are the different kind of exercises that we have done? One is we have learned how to fork. Okay. Do a Google search and find out where are the repositories, okay, who are the intelligent people or intelligent institutions which have put their code on GitHub, and we have cloned it, forked it, okay, into our private repository, and then we have installed Jupyter Notebook in our laptop and our desktop, and then using Jupyter Notebook we have executed this, and our browser application, okay, sensed is tightly linked with Jupyter Notebook. So there we have been able to execute those lines of code. Okay, so for all the computation that is done is on our own local machine. Okay, so our machine has done all the computation. It was not Google Colab, which was pointed out, which was done yesterday. Okay, it was on a local machine. So what is the drawback here? Drawback is that our machine has been tasked here. Okay, advantage is what is the advantage? Advantage is data set is with us, code is with us, so we are free to make any changes to our code. Okay, and at the end of this, okay, so in the exercise experiment itself, you might have observed, okay, in the program that was run here, there is a small button at the top which says that, which gives us an option to open in Colab. Okay, so the same code, if you press here, it will, the Colab research google.com, okay, the portal which was introduced yesterday will be opened, and to which this particular code will be fed into. Okay, so at this particular time, you do the same thing that Bashar did yesterday. I'm going to do the same thing. I'm going to connect it. Okay, and it allocates the CPUs and RAMs and disk space to me. Okay, so after doing this, I can do the same thing. Okay, go step by step. Okay, it initializes and then it is connected. Once it is connected, okay, I do the same thing that Bashar did yesterday. Okay, so it runs it. Now it is, this is being executed at in Colab. Okay, not in my machine. So it does the same thing. So here, so here the iteration is now done at Google's, okay, using Google's GPUs, okay, if it has been used. But certainly their CPUs, it's the Google's performance machines that have been exploited here. Okay. And it gives maybe different kind of values. Okay, so here the values that are provided is 98.91. Ours was 99 point something for the first one. And let's look at the test set. Okay, it will be a different value, 98.5. Okay, so okay, so these are the values here. So it might change here if I run it again once again. Okay, the values might not be the same which is shown here. It might be different. Okay, so we have seen this particular experiment done here. So what is the software engineering here? Software engineering was our ability to make use of the efforts of other giants. Okay, giants, GIANTS. Okay. So it's a kind of a collaborative work here. Okay, collaborative sharing work, where we make suppose if you want to make a modification, you make a modification and you upload it into the GitHub. Okay, it will be stored there. You can also store it in Colab or in your account, or store it in GitHub where the uploaded one, the amended one will be also be stored. Okay, and if it is a public repository, it can be used by anybody else. Okay, anybody else can pull down your code and reuse it. Okay, so by this way of sharing of code and techniques, okay, we have something similar to the Wikipedia exercise. Okay, Wikipedia is nothing but an encyclopedia of information where many people get together and do this sharing act, and the end result is you have an kind of a digital encyclopedia. Okay, which will force all other commercial proprietary encyclopedias to dust. Okay, so that's a disruption there. So encyclopedias, okay, in our young days we might have seen copies of Britannica encyclopedia. Okay, but today you will not get those stuff. Okay, nobody can market it. Today everybody has shifted to Wikipedia. Okay, so that's the power of sharing. That means, and the concept is very simple. If I have an idea, and if you have an idea, and if we are willing to share our ideas, then both of us will stand to gain at least 2 ideas each. Okay. if 10 people join together and do the same thing, each of us will have, if 10 of us has got an idea each of us will have at least 10 ideas. If more ideas can come out from combination of these ideas, it will be even better. Okay. So our effort is minimal. As numbers increase, okay, this will scale up, and is something which is very beautiful, like Wikipedia. Okay. So the same thing has been tried out on various domains also, and for here, okay, as in this software engineering part of it, we find that most of the machine learning and deep learning experiments, okay, are already there. They are taking shape now. Okay, all it needs is somebody who will create something like a Wikipedia portal, okay, for this code, and you will have an encyclopedia of, you can have, imagine, okay, an encyclopedia of all this shared code coming up. Okay, so it might be a reality in a couple of years, if not decades. So let's go back to our discussion. Okay, we still have a couple of minutes, 15 more minutes. Okay. So this is something. Now let's move on to part 3. Okay, and see how it is. How these concepts. Okay, so we have artificial intelligence, deep learning, and machine learning. Okay, all machine learning is a subset of AI. Representation learning, deep learning is again a subset of machine learning. Okay, and now let's look at on the left side. What we see is these are the visible layers. Okay, we are using it. We are just about to discuss the deep learning concepts. These are the visible input layers in the sense in which here there is an image of this particular girl or boy. I don't know. Okay, yes, it's a woman. Okay, and it's a person. Okay, and the idea, this is a deep learning model. Okay, if it is trained perfectly, it is supposed to predict whether the image is either a car or a person or an animal. Okay, so it takes inputs either a car or a person or an animal. Okay, and it generates various representations of various layers of representations, and the final layer, it comes out with the prediction whether it is it's a car or a person or an animal. Okay, so this is how it is happened. Now let's look at this. So at the base, when we started our discussion, we were given the choice of two white dots, two sets of dots. Okay, white dots and set of white dots and black dots. Okay, and it was easy for us to draw a straight line, a classifier. Okay, there. And let's look at these two systems of coordinates. One is the Cartesian coordinates in the Euclidean geometry. Okay, there you find the x and y coordinates are there. Okay, so let's look at this. You have blue dots and then green triangles. Okay, they're classified here. Now to come out with a classifier, the classifier is more likely to take the shape of a closed curve. Okay, so it could be a circle or an ellipse or whatever. But if we are aware of this, and if we change these particular values from xy, transform them into polar coordinates, okay, where r is the distance from vertex to the object, and theta is the angle that the vertex, the line takes with respect to the r axis. Okay, the x axis. Then if you are transforming this particular data, then we are more likely to have a different kind of representation of the same image, okay, same data set, where it will become easier for us to come out with a classifier. So we have a simpler classifier here, okay, for this kind of program. So what it mentions is that in most of the cases, we should be intuitive enough, okay, not to work with the given data, but to see whether there can be better representation of the data, so that the classifier will become more simpler. So our model will be much more better, much more accurate. Okay. Now, an analogy drawn from the history is that of the heliocentric model, okay, which was predicted by Copernicus and Galileo, when compared to the geocentric view, which was initially propagated by the church. Okay, so the Bible mentioned Earth as the center of the universe. Okay, it says so. I don't know. Okay, I don't know. I think even Quran also might say the same thing. Okay, so that's a geocentric view of the universe, where Earth was seen as the center. And then again, this is again a way of seeing it. Okay, it could be a model here, but it's a geocentric model where the sun rotates around all the planets, and it might give a very different kind of patterns. But if it is the moment it gets converted into heliocentric view, okay, where sun is at the center and other planets go around, then it becomes easier for us to, okay, so the classifier becomes easy, which means that for most of the data related problems, it could, we should not be satisfied with the way it is being presented here. We should try to see whether there could be some other transformations of the same data through which we will be able to generate, okay, a better representation data, which is less computationally intensive, okay. So which means it will give less load to the CPUs or GPUs or TPUs, okay, and our model will also be much more simpler, okay. Now let's look at this. Now there is a subtle difference between machine learning and deep learning. Okay, so this is again one author's perspective, not mine. Okay, what this particular author says, and I do not know which this author is. Okay, he says that in the feature extraction part. Okay, so most of the images are there. So in order to label this image, okay, you have to extract certain features, and there's a likelihood of human intervention there. Okay, so certain humans are needed to extract the features. So some kind of human intervention is required in machine learning. And classification, again, there are neural networks, okay, which will predict the object, whether it is a car or whatever it is, okay. Whereas when you come to deep learning, what it says is that there is the human intervention for extracting features is no longer required. All you have to do is give the input signal and it will do the predictions. And the number of the number of layers also, okay, is deeper, in the sense it will have more number of layers in between, hidden layers, okay. And another aspect to this is that with most of the machine learning applications, okay, feeding the model with more data will not produce an increase in performance after a certain range, okay. So after a particular performance is needed, achieved, even if you provide it with more number of samples, okay, the machine learning model is not likely to learn more. Whereas in the case of deep learning model, since there are more number of trainable parameters, it is likely to learn further, okay. So this is again one of the difference between machine learning and deep learning. One simplistic way of saying it. Okay. And the next idea is about the Gartner hype cycle, which is mostly true for many other aspects as well, where you have a hype cycle where the expectations will be very high, okay, and what comes next is a trough of disillusionment, which means most of the things that were thought to be working will not work the way it has been expected to work. But then there will be a slope of enlightenment with reduced expectations. Okay, then they will start, the production will start, and then you will find things coming up, but not the way which was expected in the earlier phase of the Gartner hype cycle. Okay, so what this particular author, again a different author, he says that the self-driving cars or autonomous cars are here. Okay, and even deep learning is at the peak of inflated expectations. Okay. So it might not deliver all the output as is being projected now. Even self-driving cars might take, okay, according to this particular author, he says that it will take at least 7 years for autonomous driving vehicles to make, okay, its presence visible in the real world. Okay. So again, perspectives. Okay, so let's look at this. So what it here mentions is, here in the first part, there are a set of features here. Okay, same face, but shades of lights are different here. Okay, source of light is shown from different angles, and if you are supposed to train a model, okay, which will capture the emotion of the person. Okay, now depending on the source of light, the face is the same, but depending on the source of light, okay, it is likely to make a wrong prediction. Okay, so perception, okay, is very hard in this kind of cases here. Okay, so these are some of the exceptional cases of exceptions which are being shown here, where it says that the models, even though they may be able to make a prediction, okay, but if we are asked to say what this cat is imagining, okay, or okay, its behavior, it is very difficult for a model to come out with.
പിന്നെ വയനാടൊക്കെ ആയതിനെ സ്റ്റാർട്ട് ചെയ്തു. ഇനി മൊബൈലിൽ വെച്ച് നമുക്ക്
Nice comment. Okay, thank you for. Otherwise, I would have fallen to sleep. Okay, so let's continue. So this is one weakness, okay, challenge for deep learning problems where they say that perceptions, actual perceptions, and that is one big challenge with autonomous vehicles, which they say that. In fact, Andrew Ng has said that he says that if a person stands on the side of the road and waves a hand, okay, the driver may be, if there is a manual driver sitting on the vehicle, the driver will be able to capture the actual, more or less the actual impression what the person is trying to convey. Maybe he wants a lift, maybe he might be hinting at an accident ahead, or maybe he wants the driver to slow down his vehicle, okay, whatever it is, or it could be a friend of the driver who is just waving a hand, okay. So that impression will be captured by the human person, human driver. But if it's an autonomous vehicle, it will get confused. It will not be able to decipher what the waving of an hand. So he says that it's a NP hard kind of a problem, which is very difficult for computers to solve. Similarly, visual understanding. If there are, say, for example, okay, what it can't, even we can't do well is say if there is a presence of mirror, okay, you'll be able to capture, okay, how many people are actually there. And we find this if you step into some of the jewelry shops or even some of the high-tech restaurants, okay, which might show more tables than what is being there, okay, or in jewelry shop it might show more jewels, more racks of jewels, okay, than what is actually there, okay. So those things are difficult for us, and it might even be difficult for the deep learning models as well, okay. Second is sparse information, okay, very little information in there, okay, humor, 3D structures, physics, and okay, what some people minds, what happens next. These things, most of the things are difficult for us. It could be difficult for the machine as well. Okay, so we'll stop here, and if there are, at the end of part 3, if there are any doubts so far on our discussion, I'll be happy to accept them.
If you have any queries, you may please ask now. Thank you, sir. Thank you so much for sharing your knowledge with us. The feedback link is provided in the chat box. Now we will have a short lunch break between 1:30 to 3. We will meet again at 3, where sir will let us know more on the topic general features, functions and application, benefits of machine learning in software engineering. See you again at 3. Please join 5 minutes prior to the time. Thank you, everyone. You may please leave now. Thank you. Good evening, everyone. Now we'll wait for 5 more minutes so that everyone else could join. Good evening, everyone. Welcome back to the last session of the day. During our last session, we had Dr. C.K. Raju sir, who shared his knowledge on the topic machine learning in software engineering. Now, he will continue on the topic general features, functions and applications, benefits of machine learning in software engineering. Over to you, sir.
Thank you, Sona. Let me continue. Okay, so in the last session, we were discussing with many black boxes. Okay, so it's time now to know what these black boxes are. Okay, so this is a simple neural network. Okay, in fact, two representations. One is a simple neural network, the other is a deep learning neural network. Okay, so difference between simple and neural when it comes here is more number of hidden layers. Okay, so let's see the first one. The red layer, these are all neurons. Okay, where where it is trying to mimic the function of a neuron in the brain. Okay, so the red buttons are the input layer, okay, represent the input layer, and the blue ones are the output layer. Okay, so we had in the first experiment a 28 by 28. Okay. Matrix, okay, which represented a handwritten code. Okay, now I'll just try to explain it a little more. Okay, let's see. Let's assume this to be that 28 by 28 matrix. So you have 28 pixels on one side and 28 pixels on the other side. Okay, and let's assume that the picture is say a sound file. Okay, let it be like this. So if you look at the first row, okay, the first row is mostly zeros, and the last line you find okay, a part of 5 coming in between. Okay, so let's assume this is the picture of 5. Okay, this is the picture of 5. That's a handwritten 5. Okay, so it should be there should be some thickness also to it. Okay, so here you have a first row, all values 0, and the last value, say there is some value here of part of 5. In the second row, again, okay, there are more initially it starts with all zeros, okay, and then there are more values of the 5 part coming in, and again zeros. Okay, so how does it appear here? Okay, now this matrix 28 by 28, I told you 28 by 28 is 784. Okay, now this is the input matrix. Okay, so there are 784 units. Okay, and the first row comes and sits on the first 28 bits. Okay, the second row comes and sits here. Okay, and so on, and the last row comes and sits in the last one. Okay, so you have many rows in between. You have 28 rows in between. Okay, each pertaining, and I told you the last value of the first row has got some value. Okay, so let's assume this is 1, which is representing a portion of 5 here. Okay, so this is how, and we can imagine. Okay, so if it's somewhere in between, okay, you'll find many zeros and a few ones, and then followed by many zeros. Okay, so if this is the case here, okay, so you'll have many zeros, some ones, okay, and many zeros, and all this there are 28 values here. Okay, so this is how the input layer is created. Okay, and the output layer, okay, in case of MNIST, okay, were cells which had values, okay, 1, 2, 3, etc. up till 9. Now, since this is 5, okay, and you had, okay, one hidden layer, okay, followed by 10 output layer. Okay. Now, each node on the input layer is connected to all the neurons of the hidden layer. Okay, so there were 512 of it. Okay, so all the 512 neurons got connected to the first one, and similarly the second one also is connected to all the 512, and so on. Okay, and also the last one is connected to the 512 nodes of the neurons of the hidden layer. So this is the hidden layer, this is the input layer, and this is your output layer. Okay. And then what we saw next was each of the values of the hidden layer is also connected to all the values of the output layer. Okay, so all the 10 outputs get connected to all the different 512 values here. Okay, and apart from this, okay, we also had one additional cell coming, which was bias. Okay, so that was how 512 plus 1, okay, was taken. So this is the bias. Okay, this is also connected to all the output cells. Okay, so this is the construction of a simple neural cell. So this is how it is constructed. Okay, and in the deep neural network it is the same. Okay, so every node in the hidden layer is connected to every other node in the next adjoining layer. Okay, and so on. Now let's proceed. So one black box is removed, which is how the connections are. Okay.
Hello.
Yes. Are there any questions?
Yeah. Is a hidden layer connected with bias or not?
Hidden layer bias is there in the hidden layer.
Because in your example you have shown, it is not showing the bias to the hidden layer. You are showing the bias to the only output layer.
Are you talking about hidden layers to bias?
Yeah.
Hidden layers to bias.
Yeah.
No, that is not there.
Bias is not in the hidden layer. Only it is on the output layer.
Output layer, yes.
Okay. Thank you.
It contains a value. It contains usually a value of say 1 is given there. Okay, so normally it takes the value of 1.
Continue, sir, please.
Okay, fine. Now, in each of these connections, okay, now what are we trying to do? We are trying to see how the model works, okay. Now, in each of these connections, there is some weights associated with it, okay. So here, the first value, okay, associated with the first value, there will be some weight, okay. Let's say if this is A0, let's say W0 is there, okay, and so on. If this is A784, you also have W784. Okay, so there are weights associated with each of those. Sorry, not here. Okay, here, this one coming here. Okay, So there are some 784. Okay, let's assume some value here. So there are values of weights associated with each of these input nodes. Okay, and together, so this 784 for A0, 784 for A1. Okay, and similarly 784 for the last one. Are all the trainable parameters, all the weights here are part of the trainable parameters. Okay. Similarly, from the output part, okay, from here also you have certain weights associated here. Okay, so there are weights associated with all these values, and the cumulative. So all these weights. Okay, so there will be large number of weights here. So that was the value of 44 lakh something that we saw in our example earlier. Okay. In the deep neural network, these number of weights, number of trainable parameters increases manifold. Okay, so here what we see is what the addition is. Bias will sit here in all of those hidden layers. Okay. Now let's proceed. Now let's see what actually the hidden layer. Let's look at the neuron in the hidden layer and how it gets activated. Okay, so the logic is very simple. When it is mimicking the brain, okay, what they say is, suppose we are given the a jasmine flower. Okay, so some portions of our neurons in the brain gets activated. Okay, when we smell it. Okay, so we will have a what do we call a desire, a pleasure. Okay, we'll feel happy. We'll feel pleased to smell the jasmine flower. Suppose decaying cell, some meat has been decaying in the backyard, and if you happen to smell it, it will be a very unpleasant odor. Okay, in those cases, those neurons which got activated during when the jasmine flower is around will not be activated. Okay, some other neurons will be activated, and we will not feel so pleased about this. Okay, so we'll have a different kind of feeling here. So that's the function that they are trying to mimic here. Okay, in the explanation. So based on some combinations of input layer, some of the neural nodes in the hidden layer might get activated. Okay. Now, what are those conditions? So let's study now what are those conditions and how it gets activated. Okay, in the mathematical sense of it. Okay. So let's assume x0 is the value of the previous node. Okay, and W0 is the weight associated with it. Okay. Similarly, x1 is the value of the node here. Okay, W1 is the weight associated with it, and so on. Now you take the sigma sum of all these weights. Okay, you take all the sigma and add a bias to it. Okay, you are adding 1 here and add a bias and give it to that. Give the output of this. Okay, output of this particular activation to the activation function. Okay, so this is the sum total of all the weights and values of nodes. Okay, the dot product, sum of all the dot products, plus you are adding a bias and you are feeding the net result to the activation function. Now the activation function, depending on how the function is defined, will output a value. Okay, between 0 and 1. Okay, in the case, most of the cases, it will be outputting a value of 0 and 1. Okay, in the case of, and that depends on how the activation function has been defined. The most popular activation functions are sigmoid, okay, tan h, etc., where the values can range between 0 and 1. Currently, there is a new activation function which is used in deep learning architecture, which is the ReLU, rectified linear unit, where the output, just a second, where the output will be the value itself. Okay, so if the value is greater than 0, the output will be that value, positive value. If the output is less than 0, it will be 0. Okay, so it has been clipped. The negative part has been clipped to 0, and the higher side, the value itself will be output here. Okay, so that's the only difference here. Now let us move. So this is a very simple thing, and there's an analogy of a brain being shown here, we don't have to worry too much about it. Okay, it just shows how and when what are the conditions for a neuron in the brain to get activated. Okay. So this is again a simplified notion. So you are getting all the dot products, which is the product of weight plus the value of the node here. Okay, which is in this case 0.7, 0.6, and 1.4. Okay, you take the sum, add the bias. Okay, and you'll get some value. You pass it on to the activation function, and the activation function, depending on the activation function, it will decide. Okay, the node will decide at this point. This particular node will decide whether to trigger or not, trigger itself or not, whether it has to pass a value to the next layer or not. Okay. In the case of sigmoid, if it passes, it will be passing a value of 1 or 0. Okay. In the case of most activation functions, the value will be either 0 or 1. In the case of ReLU, there will be a strength associated with the firing, which will be the positive value that the activation function has generated. So that's all as far as the firing of the node of intermediary layers are concerned. Now let's look at it once again. Okay, so you have the input given here, 784 values. Okay, all ranging between 0 to 1, because we are after normalization. Okay, we have divided each of those values by 255. Okay, so just to restrict its values from 0 to 1. Okay, then there is the first layer coming in. Okay, second layer coming in, and finally once you start feeding it value, there will be some predictions here. Okay, associated with each of those layers, there will be weights and bias. Bias, of course, is cannot be tuned. It has got a fixed value of 1. Okay, so these are the weights are the trainable or tunable parameters for us. Okay, let's look at it once again. Okay, it's the same. You have input. Okay, hidden layers, 2 hidden layers here, and a prediction based on the values of weights here and the bias here. Okay, you get a value of y. Now, associated with this input x, there will be a true set of values for the target y. Okay, let's assume we are showing only cats and dogs. Okay, and let's assume that we have trained all these neural networks to capture and identify all the cats, distinguish all the cats from dogs. Okay, so let's assume the value of cat, label of cat is 0, and the label of cat or dog is 1. Okay, suppose after training we are showing a picture of cat. Okay, so we are inputting a picture of cat. We are expecting there will be 2 values here. One is for cat and the other is for dog. Okay, so we are expecting 1, 0 to be the value here, where 1 pertains to cat and 0 pertains to dog. Okay, true values is again, okay, is 1, 0, because first one is cat and the second one is dog. Okay, now here in this case, the predictions and the true values. Okay, the loss function here is 0, because we have our predicted set is almost as the true target, and this is also the true target is also known as the ground truth. Okay, so the predictions and ground truth are, if it is same, the loss function will have a value of a minimal value. Okay, it will be a 0. So loss score generated will be 0 here. Okay, so there won't be any need for adjusting the weights. Okay, if that is not the case, okay, suppose predictions are wrong, which differs from the ground truth. Okay, then the loss function will generate a positive value, and there will be a loss score associated with, which will be used as an input by the optimizer. Now, optimizer is an algorithm whose role is to adjust the weights so that the loss function in the next iteration gets minimized. Okay, so this is all what is happening here. Okay, so that's the black box behind every other neural architecture. So this is the biggest black box, and once we have understood this, the rest is very simple. Okay, there are only slight modifications which come in. Now, how does this optimizer optimize it? Okay, optimize the weights. So it is done. Say, let's look at this. So this is there are various algorithms for this. This is the diagram of a stochastic gradient descent. Okay, algorithm. What it does is there is a loss function here. Here it is shown as cost. Okay, the cost function or the loss functions. Okay, in some text discussions, it's shown as the cost. Okay, somewhere it shows as the loss function and the loss score. Okay, all are the same. What it takes is associated with each weight. Okay, there are many weights associated with each weight. It takes the partial differential value of the cost function with respect to that weight. Okay, and which will give the direction of the, which will be the gradient at that particular point of time. Okay, at that particular point. So it will be directing towards the, there will be a slope. The gradient will be, direction of the gradient will be discovered here. And in that direction, the value of X gets adjusted. So in this case, the value of weight W1 will be decreased, okay, by a small amount, which is the also known as the learning rate, okay, a small step. And once it reaches the minimal value, okay, no more adjustment is needed. As far as this particular weight is concerned, okay, the cost is minimal here. Okay, so that's the trick behind the stochastic gradient descent. Okay. Now some of the other concepts here are overfitting. Okay, some overfitting or underfitting is there. Okay, so let's look at what is the case of overfitting. So what are we doing here? We are given as a few data points, okay, some pattern, and we are asked to find out an equation, okay, which fits through the data points, through most of the data points. Okay, so suppose we draw a sine curve. Okay, we find that most of it suits the sine curve as well. Okay, so if you are getting some unseen data, say suppose here in this point, if we get a data, we can come to know that it's part of this particular sine equation. If you get a value somewhere here, we know that it's not part of this particular equation. Okay, it's not part belonging to this class. So what happens is if we have large number of trainable parameters or say a small number of samples, there are chances that the equation that we generate, okay, we are optimizing the weights. Okay, so there is a possibility that we'll generate some equation like this, okay, which will pass through each and every value, okay, for the training data. So this is the training data. So you have a very high accuracy rate for training data, but say suppose we get a value in the test data for which the model has not been trained, okay, an unseen value. If it appears here, looking at it, we can identify that it belongs to this particular class, but since there has been an overfitting, okay, the model will refuse to identify it as part of this class, and it will predict it wrongly. Okay, so that's a classical case of overfit here. So what it have a 9-degree polynomial, the chances of overfitting are very high. Okay, so in the coming back to this particular neural model, okay, if you have large number of neurons in the hidden layer, chances of overfitting increases. If you have low number of samples, okay, okay, for every class, then also there is a possibility of overfitting to happen. Then how do you distinguish when there is an overfitting or not? Okay, so let's look at the blue line. The blue line indicates the accuracy of the model for the training set. So here we look at the loss. RMS is the loss function here. Okay, root mean square. So let's look at the loss value. You find that loss is decreasing, hits 0 after 9th iteration. Okay, at the end of 9th iteration, you have loss function coming to 0. But you look at the test set, okay, unseen data set. Okay, for 8th iteration, it is okay. Okay, it again improves with the model. But on the 9th one, the error increases. Error on the test set increases. Okay, at 10th one, it might again increase. Okay, so which means this particular, now what when we say about this model, all that we can say is this model is a good model. Okay, as long as we pertain, okay, we stop the training at the 8th iteration. Okay, if we take it beyond 8, even though the accuracy of the training set increases, okay, which means the loss decreases. The accuracy on the test set is on the reverse side. Okay, it decreases, accuracy decreases, and the loss is shown to be increasing. Okay, so this is not a good model if it is trained beyond 8 iterations. Okay. Now something about the actuation functions. Okay, we have just mentioned about some of the actuation functions here, which is on the hidden nodes. Okay, so this is the actuation function. Now let's see them in details. What are those different actuation functions? Okay, some of the most common ones, 3 of the most common ones. One is the sigmoid one. Okay, here is the equation. Sigma of x is 1 by 1 plus e raised to minus x. Okay, x is the function. Okay, x is the function. Contains bias plus dot products of all the weights plus input values. Okay. So that is given here, that is in place of x. Okay, you compute this value. If it is less than 0, its value, it's less than 0.5, okay, it is taken as 0. If its value is greater than 0.5, its value is taken as 1. Okay. Similarly for tan h also, and for ReLU, it's max 0, x. Okay, so x is the function that has been generated, which has been fed to the actuation function. If it is ReLU, it will fire with strength of x. Okay. If it is a negative value, it will not fire. Okay, its value will be 0. So that's the ReLU one, and this is currently being used in most of the deep learning architectures. Okay, because the hidden layer. Okay, hidden layer not only needs to, if apart from firing, it can also depict some strength to it. Okay, then more information, more valuable information will be passed on to the next adjoining layer. Okay, so that's the secret behind ReLU. Now there are loss functions. Okay, that we mentioned here. So we looked at here. Okay. Between the predictions and the ground truth. Okay, we can generate a loss function. Now there is no such thing as universal loss functions. Loss functions are determined. Again, here also, activation functions are determined. Okay, it's left to us, to the designer of the neural architecture, to choose which of these are most suitable. Okay, in certain cases, ReLU will be suitable. In certain cases, sigmoid will be suitable. In certain cases, tan h will be suitable. Okay, in certain cases, sigmoid will be preferred more than ReLU. Okay, say in certain cases like generative adversarial networks, okay, which is used to generate the deep fake images. Okay, there they say the sigmoid functions seem to perform better. Okay, so that's there. Now let's look at loss function. So loss function is it has got something to do with the difference of predicted values, set of predicted values, and the actual values which are supposed to be there. Okay. So in the mean squared error, which is largely used in the case of regression, okay, where regression is again, okay, is another kind of, okay, if you look here, okay, say suppose I have, say, housing prices. So these are my this is my housing prices. And this is the house floor. Sorry, I'll take the other way around. Okay, number of floors. Okay, number of floor space of the house, and I take this as the housing and the prices. Okay, so let's say it is 5,000 square feet. This is 10,000 square feet. Okay, this is say 20,000 square feet, and depending on the values, okay, the price of house. Okay, let's say some value here. And this is in the ascending way. Okay, so here will be value, here will have some value. Okay, and there might be some curve here. Okay, now if you're asked to, so this is a pattern. Okay, now depending on this value, okay, set of values, if you are given an unseen value, say suppose here, if you're asked to predict the value price for a house whose floor space say is 14,000 square feet. Okay. If you have a classifier, if you have generated the equations which pass through most of the data points, okay, then you'll be able to generate the corresponding y value for this particular x, okay, 14,000, you'll be able to generate. Okay. So here, this is the regression value. In cases like these, the cost function selected is usually the root mean squared value. Okay. In many other cases, it's the cross entropy loss, okay, whose definition is something like this. Okay, so what is the mean squared error? It's the difference between predicted value or the ground truth and the actual prediction, okay. Prediction and the ground truth, taking a square of it and summing all those independent values and taking the average of it. Okay, so that's the mean square error. Now, cross entropy loss is again another function. Okay, you have the ground truth, you make a multiplied by the logarithm of the prediction, taking a sum of all the classes, okay, and multiplying it by -1. So that's the cross entropy loss. So this is a function, and we can also come out with our own loss function. Okay, we can tinker around. There is no hard and fast rules here. We can also have our own loss function, and these loss functions should pertain to the problem. Okay, in certain case, if you find that the loss function that we have generated performs better, okay, then that can be chosen for that particular model. Now, how are the values adjusted? Okay, so stochastic, we have seen the case of with stochastic gradient descent. Okay, so it is adjusted a method usually known as backpropagation, which is nothing but taking the partial derivative of the function let's move on to another application in an example taken from the deep learning architecture. Okay. So this is the GitHub that I have been discussing about. Okay. So let us take another example from another set. Okay. So I am taking an experiment of STTP experiment 1. Okay. That's the code, and I've already opened one here. Okay. Same one. So this is the program which is written there, coded there. Okay. Now, what is this? So this is again, okay, a few lines of code. Okay, it contains iterations from the previous experiment. Okay. So what I'm going to do is I'm going to open this particular experiment in Colab. Okay. So this is my account in GitHub. Okay. So I have created it, and if you can also do this, create a new account, come to this my link, okay, and press this fork button. Then a copy of all the experiments will be copied onto your account, okay, and you can do the same thing that I'm using here. Okay, I'm going to open this in Colab. And here to open this in, how this button comes, I'll just explain once again. Okay, so it is opening the Colab portal. It is going to the Colab portal. I have already logged in with my Google account, so it is opening it. Okay. Now, after making changes, okay, we have a provisions to save it. Okay, we can save a copy in GitHub. So if you press this button, select this option, this particular amended code, okay, will be saved, automatically saved in the GitHub. So that's how the changes take place. Okay, which means in GitHub we save the code which is from some other repository. We open the program in Colab, run the program in Colab. Okay, if you want to make changes, we make changes and then save it using the saving option under GitHub, and it will go back to GitHub and automatically save it there. Okay, we have to carry the code also. So what I've done is I have created a data set, downloaded. Okay, initially I told you that none of the data sets that I'm using here, none of the slides, nor the code, nor the data sets are mine. Okay, I have not created anything. I just depend on God. I was depending for everything on a collaborative environment. Okay, whatever resources are available on the shared media, okay, has been used here. So what I have done here is I have downloaded rps.zip. This is a file which I have downloaded, okay, and I have uploaded it to my Google Drive. Now, what is this zip file? This zip file is a collection of is a data set here. Okay, so it contains two parts. One is the train folder and a test folder. Okay, so this is the RPS folder, contents of the RPS folder. Now the train part contains another folders, okay, each containing each named as paper, rock, and scissors. And in fact, we can name it in there are only 3 classes here. Okay, and this is a game that okay, small kids play. Okay, in my childhood I played this, but I have seen my children playing this. Okay, they are thrilled whenever they are sitting isolated and sitting alone. Okay, I see them playing this game. So what is scissor? You find a set of images here. Okay, so these are all scissors, images of scissors. Okay, so that's the picture here, and all these images are different images. Okay, they have the same dimension. Okay, this is of a fair lady. Okay, hand of a fair lady. So her complexion is fair. This is of a dark person. Okay, so complexion is little dark. Okay, so these are various ways in which the scissors are represented by different people, many other people. Okay, so all combinations of scissors, okay, are captured here, because the more the merrier. Okay, if we can get almost all the possible combinations of scissors, then we'll have a perfect model, because everything will be mapped here. But usually that's not the case. Okay, you get only sample of this, and based on this you will have to train a model. Okay, so this is my scissors. Now let's see how my rock looks like. Okay, so these are my rocks. So that's something like a hand with all fingers folded. Okay, so different kind of people, how they fold it. Okay, so these are different rocks of the people of different complexions. So whatever image can be obtained from anywhere, okay, as rocks are all pulled in and placed into the folder named rock. Okay. Similarly, for all the values for paper, okay, all the possible images for the paper, from wherever they are all pulled in and put in this particular case, okay, in this particular folder. So that's my 3 classes. Now I'm going to develop a model, okay, which will be trained on the values which are shown here in this particular case, and I will use the model to see what is the accuracy for these test cases. Now these are the test cases. Now these samples are not there in the training data. Okay, so those models are not there. So I would like to see how my model, which I have generated for using the training data, performs on this particular test data. So it's simple. Okay, so this is the rock, paper, scissors. If you have cats and dogs, there are only 2 classes you can have, cats and dogs here. If you have 10 breeds of dogs, okay, you can have 10 folders here in both test and train. And against each of those folders, all you need to pull in is different images of one particular breed of dog. Okay, so if it is Labrador, and each of those folders in the training set contain 10,000 images, you will have to have 10,000 images, different images of Labrador put inside the Labrador folder of the dogs. Okay, part of the in the training part. And suppose you have 2,000 another photographs of Labrador test on, that can be separately stored in the test folder. Okay, so this is how we build a data set. Now, to build this data set, there has to be we have to take some more precautions. All these images are supposed to be of the same dimension. Okay, so if I open this image, its dimension will be shown here. Okay. Under properties, it will show image properties. So it's a 300 by 300 pixels. So all the images should be of 300 to 300 images. So this looks like a very, have the scissors of a very beautiful lady. Okay. I don't know. Okay, I'm just guessing. Okay, so that's it. And if in the case of dog, if we have say German Shepherd, we should also be having all the images of German Shepherds in the same dimension as that of the Labrador itself. So all the images which are there, all the folders under test and training data set should be of the same dimension. Why? Because our input layer, okay, the layer that we started with, okay, the red cells, okay, so that is fixed one, okay, that should be fixed. In the one that we showed here for MNIST, it was 28 by 28, which is 784. But here, scissors, okay, it is 300 by 300, which is 90,000. Okay, so that's how. And what I've done here is after creating test and training part, I have zipped the RPS, and I created the RPS.zip, uploaded this RPS.zip to Google. Okay, and then from Gmail, from the Google Drive, I have pulled out its ID, and I have put the ID value here. So zip ID is the value of the ID that my RPS zip file, which I have stored in my Google Drive, shows. So that has been produced here. Okay. So in your case, you will also, now where do you get the RPS.zip? Just Google and find out, you will get it. Okay. So there will be some GitHub which will be carrying it. So all you have to do is download it. Before uploading, you have to verify whether the images are of the same dimension. If they are not, okay, the model will not behave correctly. Okay, it might throw some errors. Okay. So then, if on your own, when you're doing this, you after forking the code, okay, you will have to change the zip ID. Zip ID, this ID should be the ID that your Google Drive shows for the RPS.zip file that you have stored. Okay. Now, having said that, let's start. So yesterday's experiment, we are going to connect it. Okay. It is getting connected to the CPUs. Okay, and waiting for the resources to be allocated here. Initializing, and yes, connected. Now let us start. Okay. Okay, zip ID has been allocated. Now we are going to import some libraries. Now at this point, it is authenticating with the driver, with the Google Drive. Okay, and it now gives a link. Okay, so we'll follow what it says. Go to the following link. So I'm pressing the link. It wants to know whether I have access to that particular link or not. Okay, so this is my account, so I am opening it, giving access to Google Colab to my zip drive. Okay, so there is a code coming here. I am going to copy this code. I am going to paste it here. So I pasted it. Okay. If everything is correct, okay, it has been authenticated. So now it can, my application can make use of the RPS.zip file. Okay, using the ID that I have passed on to it. Okay. So creating a temporary folder. Okay. Now there are black boxes here, but you don't have to worry about too much about these. Okay, these are all make directories like temp, okay, name temp, and then you are downloading the zip file. Okay, so it is downloading this zip file. Okay, it's complete because both Colab and Google Drive belongs to Google. Okay, it's fast. it uncompresses and creates a temporary folder like temp, okay, and stores there. Okay. Now I am going to define all the classes here, okay, and I'm giving the absolute path to the classes, okay. So this has to be changed if there are more number of classes, okay. So that's common sense, okay. Anybody can do it, okay. And just to inform you, these kind of experiments are done at K2 level in USA, which means students who are studying in school, okay, below 12th standard are the ones who are using codes like this. So I have executed this. Okay. I am importing the plot we have seen yesterday, okay, and it shows, okay, it shows some of the images that are stored under rock, paper, and scissors. Okay, so having seen all the test cases, okay, now we are creating for the test set also. Pass for the test set, which will have to provide, okay, used for testing the accuracy of our model. Then we are going in for okay, using the Keras framework. Okay, we are rescaling. This is rescaling. Okay, changing all the values and the values to be between 0 and 1. Okay. So it has found 2520 images belong to 3 classes and another 372 belong to 3 classes. So the first one should be the training set and the second one should be the test set. Okay. Now this is where we are going to build. Okay, so this is a deep neural network. Okay, it contains multiple hidden layers. Okay. Now here there is some explanation might be needed. Okay, so looking at this, what we find is instead of 28, okay, we have 150, 153. Okay, 3 obviously means there are 3 channels. Okay, so for every color image, okay, there will be red, green, and blue channels. So that's three channels, and all the pixel values of all the 3 channels are mixed together. Will we see a true color image? Okay. And 150 by 150 is the image size. Okay. Okay, something else. Okay, now 60, we have the 64 value coming in here. Okay, that these are number of the different filters being used here, whose dimensions are 3 by 3. Okay, so we have a 3 cross 3 matrix, 6 of them, and each of those filters, what they do is that's the convolutional filters, and what they do is they are taken across this 150 by 150 image. Okay, and it generates a filtered output. Okay, so in certain cases, what it means is, say, suppose if we on an we have seen certain kinds of filters, for instance, most of the photo editing software will allow us to generate, say, there might be an option to generate the photocopy image of our from a real photo. Okay, so we might think how it is being done. So there are a large number of filters there. What we are doing is we are applying the filter which will generate the output of, which closely resembles that of a photocopier. Okay, so that's a filter. That filter is nothing but a 3 cross 3 matrix, mostly a 3 cross 3 matrix, whose values will be are predetermined. Okay, so if that is taken across, okay, given and taken across this 150 by 150 input image. Okay, step by step. Okay, there will be a cross product. Okay, there will be a dot product between all those values, and what we get is another matrix. Okay, whose representation will be the photocopy image that you have seen here. Okay, So its values are pre-adjusted. So there are 64 of them. So what it does, it generates all the special features. It tries to extract as many features as possible from this particular image. Okay. So there are, and next one is the max pooling layer. What it does is, and which is whose dimension is 2 and 2 by 2. So it's a 2 by 2 matrix. Okay. Okay. So what it does is, this is assume this is a 2 by 2 matrix. So let's assume after convolution we have a value of 0, 5, and 7 and 9 coming at. Okay. So what max pooling does is it looks at these 4 values and takes the maximum value here from this particular 4 input values, and then discards the remaining 3 values. Okay. So what it means is, from this, what it implies is that for an image which has been passed through filters, okay, and if there are 4 such values generated out of it, okay, all that is needed to generate the filter is this particular. Okay, it can be further compressed. So there is a 1/4 compression coming in. Okay, the size gets reduced by 1/4 with just this value, and this is all that is needed. And what they say is most of the information for this particular portion of the image will be contained in 9. So that is max pooling method. In some other cases, you take the applications, they take the average pooling. Okay, so most all other combinations possible. The other one that I told you about the convolution is, so you have a 150 by 150 matrix. Okay, and another 3 by 3 matrix whose value may be, no, I'm just guessing, 0, minus 1, 0, 0, 0, okay, 2, 1, 0. Okay, so suppose my filter value is this. Okay, it might, what I do is I will place on top of the first leftmost corner. Okay, I might add certain values or some pad values here. Okay, so that I can get the convoluted value for the first pixel also. Okay, and then I place here. Okay, and then what I do is I take a dot product of each of those matrices. So here is a 3 by 3 matrix. Here is a 3 by 3 matrix. Each of those matching cells are multiplied, and it's sum taken. Okay, and value put here, and that will be a value. Okay, so similarly, after getting all those values, the pictorial representation of this particular part will be the filtered output. Okay, and this is the filter. Okay, so suppose we have a photocopier. Okay, so photocopier thing coming out. If this value pertains to photocopier, what we actually get, okay, when we give our photo is a photocopier type of output pertaining to our face. Okay, that's it. So nothing much about it. They are all different filters. Okay. We were here. Okay, no, we were into the experiment. No, sorry, not here. Here. Okay, so that's it. And then we read that, okay, 3 or 4 times, so it is repeated. And here ReLU is used, which is the activation function. And in the last one, we have the activation function of softmax. So we have how many outputs are there? 3 outputs are there. So when we say softmax, the value should be between, okay, it would be 001 or 010 or 100, depending on the case. Okay. Now, this is a sequential model, which means all these layers are stacked one on top of the other. Okay, so that's sequence. They are placed in sequence. So how many layers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 layers. Okay, so that means layers plus input layer is 13. Okay, so many layers. Now let's look at what is being done. No, sorry, this is not a layer. Flattening is okay, connecting every node to the next node. Okay, and dropout is one thing which is used to reduce the pore fitting part. Okay, so most of the time I informed just before that if you have more number of nodes coming in the hidden layers, there is a chance, every chance for the model to be performing displaying the pore fitting part. Okay, so So to avoid overfitting, we can introduce the dropouts. Okay, so if 0.5 means 50% of the hidden nodes of the hidden layer are dropped, simply dropped. Okay. Now let's execute this and see what happens. Okay, so there's a model summary coming up. Let's look at this. How many trainable parameters? If we find that there are 3 million plus trainable parameters. Okay, so all these parameters, how are these? Which is the function responsible for training this? It is the optimizer. Okay, and why does optimizer do this? Because there will be some positive value coming out from the loss function. Okay, as loss score. So in order to reduce the loss score, the optimizer will try to again change the values of any of these 3 million weights. Now let's try to. So here the optimizer used is RMS prop. Okay, so it's a root mean square which is taken. Loss function is the cross categorical cross entropy. Okay, and metrics. Okay, as we have seen from our earlier example, is the accuracy metrics. Okay, now let's see how it does format. Now this model, what I'm doing is I'm going to save this model. Okay, once we generate a model, it contains all the weights, and that weights is all that we need. Okay, to take it outside this particular Google Colab. And if you want to port it into any other device, so say suppose I want to put it in my mobile phone and use my phone to check whether if the image that I point to is a raw processor, I can use it. Okay, so that's why this contains the weights. Okay, I'm going to execute this. Sorry, there are 25 epochs and that might take long time. Okay, so I'm going to reduce. Sorry, optimizer. Okay, let's stop. It won't stop. Okay, stopped. I have reduced it to 5 times. When I'm making the number of epochs is nothing but a number of times the optimizer sees all the data, all the training data samples. So at the end of first round, we have accuracy on the training 0.45. On validation accuracy 0.8. It improves. It is likely to improve with everything, but it might not be very high figure. Okay, so we have reached at the end of this. Okay, we have a validation accuracy close to 1 and a training accuracy close to 90%. Okay, good. Now let's look at the plot of the curve, the accuracy validation loss. Okay, so we come here, we find that red is the training accuracy, it continuously increases. Okay, validation accuracy shoots up. Okay, so what can we infer from this is that most of the unseen data, okay, something close to it might already be there in the training data. Okay. That's the best inference that we can get from this particular image. The next time if I execute this, I might get a different curve. Okay, It depends on what portion of the training data has been appropriated as the validation set also. Okay. Now, having generated this model, okay, we can also check whether this model functions on other unseen data. Okay, so that's the code here. Okay, so I'm going to browse my test samples. Okay. This is my test samples. Okay, I'm going to take, say, some figure. Okay, so these are the images which are not there. Let me take this one. And it has been given here. So model examines it and outputs a value 0, 1, 0. Okay, so that was rock. Okay, so rock came out as 0, 1, 0. We were rock, paper, scissors. Why? Is this correct or not? It is correct because the RPS, even though is mentioned this at RPS, it takes in the alphabetical order. So the first category is paper, R, and then P, and then comes PQ R. Okay, then comes R, and the last one is S. Okay, so it is paper, rock, and scissors. So it has predicted that it is rock correctly. Okay, so we have a correct prediction. Let us check once again, okay, for a different sample. This time, let's check from scissors. Okay, the beautiful pair of hands, and it should come as 001. Okay, so our model functions correctly, and we are supposed to get, okay, very high value for our unseen data. Okay, so which means we have generated a fairly good comprehensive model with just 5 rounds of training. Okay. Now that completes our discussion. I'll just quickly wind up. Okay. So we demonstrated here. Okay. And now let us look at what all we have been exposed to so far. Okay, we have seen yesterday also we have seen Google Colab. Yesterday entirely it was Google Colab. Today we have seen code getting how to share code or use code from GitHub or GitLab. Okay, so most of the sources are already there. Okay, all that we have to do is customize it. Okay, test it and then customize it. We have also seen Jupyter Notebook, which is an application which runs environment which runs on which can be installed in our local desktop or computers. And then we have seen even yesterday also, okay, yesterday it was Pandas framework, okay, today it's the Keras framework, okay, it's a high level framework. And then even yesterday and today we have seen the Python and associated libraries, okay. Now that completes our discussion. Are there any questions or something to add? If there are knowledgeable people here, you can also add. Okay.
Somebody was raising their hand.
Pardon?
Somebody was raising their hand.
Somebody is asking a question.
Yeah, raising the hand I have seen a couple of minutes before.
Yeah, anything. Yes, hands are welcome.
Sir.
Yes, please.
What is the role of learning rate in the network?
Learning rate, I told you, that is when you are using the optimizer, you have seen the step function. Okay, how fast should we descend? Should this algorithm descend to the minimal point? Okay, so the learning rate is a measure of the step function. How much should it jump into? How much should it adjust itself? What value?
If we are taking the
if it's a high value, then it will oscillate. It might oscillate around the global minimum. Okay, so it might not reach the minimum value. It might cross and go to the other side. Okay, so there is a possibility of hovering around minimum. It might not reach the minimum. Okay, if it is too low, then it might take too much of time to converge and reach the global minimum value.
Okay, sir. Thank you. Thank you.
Welcome.
BG, he was raising the hand, it seems. BGKP? BGKP? She's not there.
It might be wrongly pressed also, or she.
Okay, fine.
If anyone have any doubts, they may please ask right now.
Oh, I have my director also here. Sir, sir, good evening. Long time, sir.
Participants, please try to get maximum information. He is very experienced in this area. Hari, anything to ask? Hari, listen.
In Java, ये
Yes, sir, please.
कौन सा है बी फिफ्थ सेमेस्टर है बीटेक फिफ्थ सेमेस्टर सीएसई की है सर
Raise Ahmad.
Excuse me, sir.
इसी एक मिनट सर फिर देखो इसी के स्टूडेंट पढ़ रहे हैं
हाँ सोनक वाली.
यस सर ये डॉक्टर पॉल है
Please mute to the line.
Could you tell me some information?
I think he was asking some question.
Sir, please unmute yourself. Your question was not audible, sir. Rais Ahmed, sir, your question was not audible.
Hello.
Yes, sir,
yes,
you're audible
please go
right
ahead.
now.
I want to ask you the one question. What is the MACPIT neural network?
Those are the classical models. I have not. See, initially when I started, I told you these are all comparisons. Okay, people are trying to compare with the neurological cells, biological cells. Okay, so that I think is the first. I think it has got to do with the history of this particular neural stream. But in the when it comes, you asked another. You are opening up another domain of discussion. Actually, this discussion of. Can you please mute your this thing? There is some noise getting.
Some.
Yeah. Yeah, Raju, please continue.
Hello.
No, he has got another question. Okay, raise another question.
Yeah. Sir, there are some excitatory and inhibitory weights are there in the NIMET. So I want to what are these the weights? How we adjust these weights?
These are classical models, and I am not. I can't recall as of now.
Okay, sir. No problem, sir. No problem.
But the other part is a larger discussion that has come up now is those were the ideas that the mathematicians built these neural models on earlier on.
Yeah.
Right now, what has happened is this has gone beyond the statistician's domain. Okay, so this particular application stream has grown beyond statistics. It cannot. Many of the experiments that we do now cannot be explained using pure statistics. Statistics still has to catch up with it. Okay, if at all they want to. It has become what Francois Joliet, okay, the founder of Keras, says is that this particular stream has become the domain of what is known as trial with experimentation. What do we say? Okay, that's a particular. Just like medical stream, the medical people will not be able to explain if you take a paracetamol and if the fever subsides. Okay, they will not be able to explain in terms of at any level how this actually works. Okay, so from the No, there's a particular word associated with it. Okay, phrase associated with it. So from the explanatory side of view, it has gone away from the RANds, and now the results actually validate the experiment. Okay, so if we have a model, and if we can use that model to validate our experiment, okay, so that stands now. So you don't have to compare it with the statistical models, on you don't have to compare even with biological neural network. Okay, your experiments itself, the results of the experiments itself is a validation that your model is correct or not. So it has gone away. Okay. That's how it is evolving into.
Should I have one question? One
You,
more
yeah,
question?
you can add. Okay, you can add a race onto something if you know, or ask another question. Yeah, please.
Yeah. We have stated we have to give the bias to all the layer except input layer.
Yes.
So yeah, in the your example, you didn't put the bias to hidden layer. So can
Bias to
hidden layer?
bias.
We have to give the bias to all layer except input layer.
Yes, correct.
Yeah. So in the example, I have not seen the bias to the hidden layer, but you have putting the bias to only output layer.
No, it's an hidden layer. Here, this is my hidden layer. This is the bias. So it's in the hidden layer.
So in the if there is a hidden layer is there, then we have to give the bias to hidden layer as well as bias to the output layer. May I right?
No, no, not to output layer. Output layer is the fixed values. Okay, so it cannot be changed. If there are three classes, there will be only three outputs. There is no need for bias here.
Okay, sir. Tell it. Okay, thank you very much, and thank you for respond me. Okay, thank you,
Okay.
Bas. Okay, thank you very much.
Anyone else? Anyone else?
The part that you maybe raise, maybe bias to input layer is there. Bias to input layer. Okay, so that is something that I missed. It to input to output layer it is not there. To input layer it is there, and hidden layers also it is there.
Sir, we have studied. Hello.
Yes, please.
We have stated if there are three layer,
Ah.
we have to give the bias to all layer except input layer. If
It might not be input layer, it might be output layer.
output layer as well as hidden layer also. We have to
No,
give the bias to hidden layer and as well as output layer.
that might not be correct. I think it is to input layer, bias should be added to input layer as well as hidden layers, not to the output layer.
Okay. Okay.
Any more questions from the audience?
Sir, I am happy to see the directors are also and other dignitaries of your college because I am from the BITS Ranchi, that you know, Birla Institute of
Oh,
Technology Ranchi.
okay, great, great. It's great to meet you.
Thank you and very much. Thank you very much. And to see the all the director and principal sir and everybody is joining to us. And thank you very much, sir.
Thank you. That's some words for us, if possible.
Sir, please.
Director is MTech from IIT Chennai and PhD from IIT Chennai.
Mashallah.
He's a hot rod. And I used to spend most of my time sitting with him, learning from.
That's your mic is mute, I think. Okay. So that's mic is muted, I think, sir. That's your mic is muted. So, I don't know.
Director sir's mic is muted. Sir,
Shall we wind up? Anything else?
Yeah.
Announcements and other things.
Yes, sir. Shall I
Yeah,
continue,
please.
sir?
Yeah, please.
Thank you, sir, for your inspiring and informative session. We convey our gratitude to you, sir, for taking your time out of your busy schedule to come here and spend it with each and everyone here. The feedback link is provided in the chat box. There is a gentle reminder for everyone. Attendance of the participants will be taken via Google Meet, and the participants with more than 80% attendance will receive the certificates. Thank you, everyone. We'll meet again tomorrow where we have the session on Introduction to Smart Grid by Dr. J.G. Singh from Asian Institute of Technology, Bangkok, between the hours 10 to 11:30. And then we have Professor Kurupat from Muthoot Institute of Science and Technology between the hours 12 to 1:30 and 3 to 4:30 to talk about the topic Machine Learning in Smart Grid. We have prepared a series of inspiring sessions just for you. By this, we come to the conclusion. Thank you everyone for your time. Wishing you a good evening and good night. This is me, Sona Shaukat, signing off. Thank you. You may please leave the meeting now. Thank you, everyone.
Thank you, madam.